Imagine a continent so ancient, so isolated, so magnificently strange, that the creatures living upon it seem to belong to an entirely different world entirely. A land where mammals lay eggs, where the deadliest snake on earth glides silently through golden grass, where a bear-like creature sleeps 20 hours a day on a diet that would poison almost any other animal alive. A place where rivers run dry for years, then explode overnight into silver highways teeming with life. A continent that has been cut off from the rest of the world for tens of millions of years, quietly engineering some of the most extraordinary, most bizarre, most breathtakingly beautiful animals that have ever drawn breath on this planet. That place is Australia. And once you truly understand what lives there, and how it survives, you will never look at the natural world the same way again. Welcome to Wild Australia, Secrets of an Ancient Continent. This is the story of a land that refuses to be ordinary. A land of fire and flood, of scorching red deserts and ancient dripping rainforests, of creatures that have solved the impossible problems of survival in ways that science is still struggling to fully comprehend. From the thundering red kangaroo bounding across the shimmering outback horizon, to the tiny thorny devil drinking water through its very skin, to the platypus hunting in total darkness using electric signals that its prey cannot hide, Australia is a living laboratory unlike anything else on Earth. Please let us know in the comments where you are watching this documentary, and what time you are watching it. And be sure to subscribe to the channel for future videos. Now let us begin. To understand why Australia is so extraordinary, we must first understand where it came from. We must travel back through time, not thousands of years, but hundreds of millions of years, to a moment when the continents of Earth looked nothing like the maps we know today. Long before the first kangaroo ever bounced across a red sand dune, long before the first eucalyptus tree stretched its silver leaves toward an ancient sun, Australia was part of a massive supercontinent called Gondwana. This enormous landmass included what we now call Antarctica, South America, Africa, India, and Australia, all locked together in a single colossal embrace. For tens of millions of years, the animals of Gondwana evolved together, sharing the same vast territory, migrating freely across landscapes that no longer exist. But the Earth is never still. Deep beneath the surface, the great tectonic plates that carry the continents are always in motion, always grinding and shifting and pulling apart. And around 90 million years ago, the breakup of Gondwana began in earnest. Slowly, almost imperceptibly at first, Australia began to drift away from Antarctica. It was a separation measured not in miles per year, but in centimeters. Yet over millions of years, those centimeters added up to an ocean. By around 45 million years ago, Australia was an island continent, completely surrounded by sea, drifting northward on its own geological journey through time. And this isolation, this profound, total separation from the rest of the world's landmasses, would prove to be the single most important fact in the story of Australian wildlife. Because when you cut off a continent from the rest of the world, you do not simply stop animals from leaving. You also stop them from arriving. New predators cannot come. New competitors cannot establish themselves. New diseases cannot sweep through populations. The creatures already living on that isolated continent are left, generation after generation after generation, to evolve entirely on their own terms. What happened over those tens of millions of years of isolation is nothing short of miraculous. The mammals of Australia took a completely different evolutionary path from the mammals of the rest of the world. Elsewhere on the planet, placental mammals, the kind that carry their young inside the womb for long periods and give birth to relatively developed offspring, came to dominate virtually every ecological niche. In Australia, it was the marsupials who ruled. These animals, which give birth to tiny, underdeveloped young and then carry them in pouches until they are mature enough to face the world, diversified into an astonishing array of forms. Kangaroos and wallabies filled the ecological role that deer and antelope play elsewhere. The Tasmanian devil became the continent's top mammalian predator in the absence of wolves or lions. The koala evolved to exploit a food source, the toxic eucalyptus leaf, that virtually no other creature on Earth can digest safely. And in the rivers and streams of eastern Australia, the platypus evolved into something so strange that when the first specimens were sent back to scientists, those scientists assumed they were looking at an elaborate hoax. But Australia's story of isolation is not only about marsupials. It is about an entire ecosystem, an entire biome, a whole planet's worth of ecological experimentation, compressed into a single landmass. And it is about the landscapes themselves, because the environments of Australia are as extraordinary as the animals that live within them. Australia is the world's sixth largest country by total area, covering nearly 3 million square miles of land. It is a continent of staggering contrasts. In the center, the Great Red Center, the Outback, lies one of the most formidable deserts on Earth. Temperatures here regularly exceed 120 degrees Fahrenheit. Rain may not fall for years at a time. The soil is ancient, leached of nutrients over millions of years of weathering, stained red by iron oxide, cracked into intricate patterns by relentless heat. Yet even here, even in this seemingly lifeless furnace, life not only survives, it thrives, adapted to the extremes in ways that border on the miraculous. In the far north of the continent, the tropical regions of Queensland and the Northern Territory receive monsoon rains that transform the landscape entirely between seasons. In the wet season, vast floodplains disappear beneath sheets of water. In the dry season, those same plains crack and bake under a relentless sun. Along the northeastern coastline, the ancient rainforests of the wet tropics cling to the slopes of mountain ranges, so old and so undisturbed that they contain plant species whose relatives appear only in the fossil record. And to the south, temperate forests and coastal heathlands give way to the cold, windswept landscapes of Tasmania, an island state separated from the mainland by the Bass Strait, where some of the most isolated and unique wildlife on the continent has found its last refuge. This is the stage upon which our story plays out. Ancient, extreme, endlessly surprising. And now, it is time to meet its cast. Let us begin where the drama of Australian wildlife is perhaps most immediately visible and most immediately striking. Let us begin in the Outback, that vast red ocean of desert and scrubland that makes up the great interior of the continent. And let us begin with the animal that has, more than any other, come to symbolize Australia itself in the minds of people around the world. The red kangaroo stands as the largest marsupial on Earth. A fully grown male, known as a boomer, can stand nearly 6 feet tall when he stretches to his full height, and can weigh as much as 200 pounds. He is a creature of extraordinary physical presence, his body built along lines that seem almost sculptural in their efficiency, his powerful hind legs and long, muscular tail giving him a silhouette that is instantly recognizable to anyone who has ever seen a picture of Australia. But beyond its iconic status, the red kangaroo is one of the most remarkable survival machines that evolution has ever produced. Every single aspect of its biology has been shaped by the demands of life in one of the most hostile environments on Earth. The scientific name of the red kangaroo, Osphrenta rufus, translates roughly to the reddish one who digs, a reference not only to its magnificent rusty coloring but to the behavioral adaptations that allow it to survive the brutal heat of the outback. But it is the kangaroo's most famous feature, its ability to travel enormous distances at high speed, that deserves our closest attention. Because in this feature lies one of nature's most elegant and counterintuitive engineering solutions. A red kangaroo moving at full speed across the desert floor is not simply running. It is bouncing. Its great hind legs store elastic energy in long tendons that work like biological springs, loading up energy during the downward phase of each bound and releasing it explosively as the animal pushes off again. This means that unlike virtually every other large animal on Earth, the red kangaroo does not expend more energy per stride as it goes faster. Instead, at its most efficient cruising speed, around 13 to 15 miles per hour, the kangaroo is essentially getting a free ride. The tendons do much of the work, and the animal's muscles simply fine-tune the movement and maintain stability. At higher speeds, up to 40 miles per hour in short bursts, the mechanics shift somewhat, but even here the efficiency remains extraordinary. This matters enormously in the context of the outback. When food and water are scarce, when a drought has stripped the land of vegetation across a vast area, survival depends on the ability to travel long distances between resources without burning more calories than you can afford to spend. The kangaroo's locomotion solves this problem beautifully. It can cover distances of many miles in a single night's foraging journey and arrive at its destination having expended less energy than a similarly sized quadruped would have needed for the same trip. Studies have confirmed that a kangaroo carrying a joey in its pouch shows almost no additional energy expenditure, because the joey is essentially getting a free ride, its weight absorbed and neutralized by the same elastic bounding mechanics that make the mother's movement so efficient. But locomotion is only one piece of the red kangaroo's survival puzzle. These animals have also evolved sophisticated strategies for dealing with the thermal extremes of the desert. On the hottest days, when the ground temperature can reach levels that would blister human skin and the air shimmers with heat haze that blurs the horizon into unreality, red kangaroos seek shade and enter a kind of behavioral dormancy. They lie flat on the ground in the shadows beneath mulga trees or rocky outcrops, their bodies pressed against the slightly cooler soil, conserving energy and minimizing water loss. They pant to cool themselves, and they lick their forearms, where a network of blood vessels runs close to the surface, allowing evaporative cooling to draw heat away from the circulating blood. Their physiological thermoregulation is equally impressive. A red kangaroo's kidneys are highly efficient, capable of concentrating urine to a degree that significantly reduces the water lost through excretion. Their feces are dry, another water conservation strategy. And remarkably, a female red kangaroo has the ability to delay the development of an embryo, a phenomenon known as embryonic diapause. After giving birth to one tiny joey, which crawls unaided to the pouch and attaches to a nipple, the female can have a second embryo waiting in a state of suspended development inside her reproductive tract. If the suckling joey dies, or when it eventually leaves the pouch permanently, the dormant embryo reactivates and begins developing immediately. This means that a female red kangaroo can, under good conditions, be simultaneously nursing a joey outside the pouch, carrying a joey inside the pouch, and gestating a dormant embryo, a remarkable feat of reproductive multitasking that ensures the species can respond rapidly to favorable conditions when they occur. And when conditions are favorable, when the rains have come and the desert has transformed overnight into a sea of green, the red kangaroos take full advantage. They congregate in the areas of highest food abundance in groups called mobs, sometimes numbering in the dozens. The males, their rusty red coats gleaming in the desert light, compete for access to females through elaborate displays and, occasionally, through outright combat. Two rival boomers facing off is one of the most impressive spectacles in the Australian outback. They stand upright, balancing on their tails, and deliver powerful blows with their hind legs, kicks of extraordinary force delivered with taloned feet that could disembowel a less armored opponent. These fights are rarely fatal, but they are intensely physical, and only the strongest, most experienced males win consistent access to females. The red kangaroo's relationship with the landscape is not merely one of passive adaptation. These animals shape the environment in which they live. Their grazing influences the composition of desert vegetation. Their movement patterns determine which plants get browsed and which are allowed to grow undisturbed. And their presence serves as a critical food source for Australia's apex predators, most notably the dingo, the extraordinary wild dog that functions as the outback's primary regulator of ecosystem health. The dingo arrives in Australian natural history like a ghost from another world. Unlike the kangaroo, the wombat, the koala, and the platypus, the dingo is not a product of Australia's tens of millions of years of isolated marsupial evolution. It is a relatively recent arrival, brought to the continent by humans somewhere between 3,500 and 4,000 years ago, most likely by seafarers from Southeast Asia who traded and interacted with the indigenous peoples of northern Australia. And yet in those few thousand years, the dingo has embedded itself so deeply in the Australian ecosystem that it now functions as a keystone species, its presence or absence rippling through the food web in ways that affect everything from kangaroo populations to the abundance of small native rodents. The dingo, classified scientifically as Canis familiaris dingo, occupies a fascinating biological position. It is not a wolf, though it descended from wolf-like ancestors. It is not a domestic dog in any meaningful behavioral or ecological sense, though it shares ancestry with domesticated canids. It is something in between, and something distinctly its own. After thousands of years of living wild in Australia, breeding freely and surviving by its wits, the dingo has developed a suite of physical and behavioral characteristics that set it apart from both its domesticated relatives and the wolves of other continents. Physically, the dingo is a medium-sized canid, typically weighing between 22 and 44 pounds, with a lean, athletic build that speaks eloquently of its lifestyle. Its coat is most commonly a sandy golden yellow, though individuals with black and tan markings and even pure white coloration exist in different parts of the continent. Its ears are large and permanently erect, giving it an alert, intelligent expression that is immediately apparent to anyone who observes these animals in the wild. And those large ears serve a purpose. The dingo's hearing is extraordinary, capable of detecting the subtle sounds of prey movement at distances that would be inaudible to a human being. What makes the dingo particularly remarkable, however, is not its physical attributes but its social intelligence and ecological role. Dingoes are highly social animals, living in family groups that can range from pairs to packs of up to 12 individuals. These packs have defined territories that they patrol and mark with scent, and they communicate through an elaborate repertoire of vocalizations that includes howls, yips, and a range of softer sounds used in close social interactions. Unlike domestic dogs, dingoes rarely bark. Their howl is their signature vocalization, a sound that carries across the desert night for extraordinary distances, allowing pack members to locate one another, and informing neighboring packs of territorial boundaries. Pack hunting is the behavior that gives dingoes their ecological power. A single dingo is a capable predator of small to medium-sized prey, rabbits, rats, lizards, and birds falling readily to a solitary hunter. But when a dingo pack coordinates its efforts against larger prey, the results are spectacular. Working together with clear role differentiation, some individuals driving prey while others circle to cut off escape routes, dingo packs regularly bring down animals many times their individual size. Red kangaroos, sheep-sized macropods, emus, and wombats all fall prey to coordinated dingo hunts. The level of tactical awareness these hunts require is impressive. Individual animals seem to anticipate the movements of their packmates without visible communication, responding to subtle cues of body language and positioning to maintain the integrity of the chase. The ecological importance of the dingo becomes most apparent when you examine what happens in areas where dingoes have been removed or suppressed. Across large parts of southern and eastern Australia, the construction of the famous dingo fence, one of the longest structures ever built by human hands, stretching more than 3,000 miles, has created a natural experiment in dingo absence. North of the fence, where dingoes roam freely, kangaroo populations are kept in check, and the vegetation that kangaroos browse is consequently more diverse and abundant. South of the fence, where dingoes are absent, kangaroo populations explode, and overgrazing can cause significant damage to fragile desert vegetation. But the effect goes deeper than kangaroos alone. In the absence of dingoes, populations of introduced predators, particularly red foxes and feral cats, also increase dramatically, because dingoes normally suppress these smaller predators through competition and direct predation. And when foxes and cats become abundant, the small native mammals, the little marsupials and native rodents that are among Australia's most vulnerable species, suffer devastating consequences. The dingo, in short, is what ecologists call a trophic cascade effect. Its presence at the top of the food chain sends ripples of influence downward through every level of the ecosystem. Remove the dingo, and the whole system can shift into an entirely different state. Restore the dingo, and balance reasserts itself, sometimes in ways that are subtle and take years to manifest, but always in ways that move the ecosystem toward greater health and diversity. Watching a pack of dingoes hunt at dawn across the flat red plains of the Outback is an experience that communicates this ecological power viscerally. The coordination, the intelligence, the absolute commitment of each animal to the shared enterprise of the hunt, speaks to millions of years of canid evolution shaped toward this exact purpose. These are not pets. These are not wolves in a strange landscape. These are Australians, As surely as the kangaroos they pursue, shaped by the specific demands of this specific continent into something uniquely powerful and uniquely irreplaceable. From the grandeur of the Outback and its great predators, our story moves to the coastal environments of southwestern Australia, where the scrubby heath and rocky shores of Rottnest Island, a small island near the coast of Western Australia, harbor one of the most endearing animals on the continent. The quokka, Cetonix brachyurus, is a small wallaby, roughly the size of a domestic cat, with a round, compact body, small rounded ears, and a face that seems, to human observers, to be perpetually wearing a broad and contented smile. This famous expression, the quokka selfie, has become one of the most celebrated wildlife photography experiences in the world, with the animal's apparent cheerfulness making them irresistible to visitors, is not, of course, a genuine emotional expression in the human sense. Quokkas do not experience happiness or contentment in ways that we can directly measure. But the arrangement of the muscles around the quokka's mouth and jaw, evolved for entirely functional reasons related to feeding and facial mobility, does create an appearance of good-natured geniality that is difficult to resist. And in a deeper sense, the quokka's success in its island environment does suggest a kind of ecological contentment, a species that has found a niche in which it can thrive, and has been doing so for a very long time. The quokka is a nocturnal animal, spending its days resting in the shade of dense vegetation and emerging at night to forage. Its diet is broad and opportunistic, including a wide variety of grasses, leaves, stems, and bark. This dietary flexibility is an important survival strategy in environments where food resources can be patchy and unpredictable. When the most palatable food items are scarce, the quokka can switch to coarser, less nutritious plant material, processing it through a digestive system that is capable of extracting adequate nutrition even from relatively poor quality vegetation. Like other marsupials, quokkas give birth to tiny, underdeveloped young that make the perilous journey to the mother's pouch. A quokka joey is born after a gestation period of about 27 days, and it is at that point less than a centimeter long, essentially a fetus with functioning forelimbs strong enough to climb through the mother's fur to the pouch entrance. Once inside the pouch, the joey attaches to one of 4 nipples and remains there for about 6 months, growing and developing in the warm, protected environment of the pouch. After emerging from the pouch, the young quokka continues to be suckled for several more months, gradually transitioning to solid food as its digestive system matures. What makes the quokka's island existence particularly interesting from an evolutionary perspective is the effect that island living has had on the species over generations. Rottnest Island, where the largest population of quokkas now lives, has no natural predators capable of threatening the adult animals. The predators that would normally keep quokka populations in check on the mainland, dingoes, large monitor lizards, and others, are absent from the island. And while this has allowed the quokka population on Rottnest to thrive, it has also resulted in these island quokkas showing significantly reduced fear responses to potential threats compared to their mainland relatives. They approach humans without hesitation, investigate novel objects with curiosity rather than caution, and show a general relaxation of the vigilance behaviors that mainland quokkas must maintain constantly. This behavioral difference between island and mainland populations is a beautiful illustration of how quickly evolution can act when selective pressures change. Within the relatively few thousand years since quokkas first colonized or were isolated on Rottnest Island, natural selection has been able to relax the costly physiological and behavioral investment in predator wariness, simply because that wariness no longer confers any survival advantage on the island. The animals that spend less energy on vigilance have more energy available for reproduction, and over generations, the relaxed vigilance trait becomes more common in the population. On the mainland, however, the situation for quokkas is far less comfortable. The species has experienced dramatic range contraction over the past 2 centuries, largely due to habitat destruction, the introduction of foxes and cats, and changed fire regimes. The healthy island populations provide a vital reservoir for the species, but the long-term challenge of re-establishing quokkas across their former mainland range remains one of Australian conservation's ongoing projects. Now we venture away from the dry scrub and the coastal heath and into the cool, clear streams and rivers of eastern Australia, to meet an animal so strange that even a zoologist familiar with all the world's wildlife diversity would struggle to fully accept what they were seeing if they encountered it for the first time. We come now to the platypus, Ornithorhynchus anatomus, the animal that broke every rule and rewrote the textbooks, and that continues, to this day, to astound scientists with new discoveries about its biology and capabilities. When European scientists in the late 18th century received the first preserved specimens of the platypus from the newly colonized lands of Australia, their reaction was almost universally one of disbelief. Here was an animal that appeared to have the bill of a duck, the body of an otter, the tail of a beaver, and the feet of a web-footed swimmer. It had dense, waterproof fur of a deep brown, beautiful and soft to the touch. It was clearly a mammal in many respects. Yet examination revealed that it laid eggs, a characteristic previously associated only with birds and reptiles. The males, it turned out, possessed venomous spurs on their hind ankles, making them one of the very few venomous mammals on Earth. The venom, capable of causing excruciating pain in humans and potentially lethal to smaller animals, is delivered through grooved spurs and is used primarily in combat between rival males during the breeding season. And then there was the bill. That extraordinary, leathery, duck-like bill, which looked like a piece of soft rubber rather than the hard keratin structures of bird beaks, turned out to be perhaps the most sophisticated sensory organ possessed by any mammal on Earth. The platypus hunts almost entirely by electroreception, the ability to detect the extremely faint electrical fields generated by the muscle contractions of its prey. Shrimp, insect larvae, worms, and small fish all generate these electrical signatures as they move, and the platypus's bill is lined with tens of thousands of electroreceptors and mechanoreceptors that can detect these fields with extraordinary sensitivity. When a platypus dives beneath the surface of a stream, it closes its eyes, ears, and nostrils, sealing itself completely from the sensory inputs that we would consider essential to navigation and hunting. It moves through the water in a characteristic side-to-side sweeping motion with its bill, essentially scanning the water column and the bottom sediment for electrical signals. When it detects the electrical field of a buried shrimp or a hiding worm, it pinpoints the location with remarkable precision and digs it out with the bill. It stores the captured prey in cheek pouches, then returns to the surface to process its meal, because the platypus has no stomach in the conventional sense. Its esophagus connects directly to its intestine, and digestion occurs through a simpler process than that found in most mammals. The electroreception system of the platypus is so sensitive that laboratory experiments have demonstrated these animals can detect the electrical fields generated by artificial dipole sources at levels equivalent to the fields produced by small crustaceans. The spatial resolution of the system is such that a platypus can determine the direction and distance of a prey item with enough accuracy to locate and capture it in complete darkness, in turbid water, with no visual, auditory, or olfactory input whatsoever. It is a sensory system of extraordinary elegance, evolved over tens of millions of years in the dark, sediment-laden streams of eastern Australia. The platypus is also remarkable for its reproductive biology, which provides a living window into the evolutionary history of mammals as a group. Like all monotremes, the group of egg-laying mammals that also includes the echidnas, the platypus lays small, leathery-shelled eggs rather than giving birth to live young. The female digs a long burrow in a riverbank, sometimes extending more than 60 feet into the earth, and creates a nesting chamber at the end which she fills with wet leaves and grass. She lays 1 to 3 eggs, curls her body around them to incubate them, and after a period of around 10 days the eggs hatch. The emerging young are tiny and helpless, barely formed, and they suckle milk from their mother through patches of skin on her abdomen where milk seeps through specialized pores. Platypuses have no nipples. The young lap milk directly from the mother's fur. This reproductive system, intermediate in some ways between the egg-laying of reptiles and the live birth of other mammals, is not a primitive or inferior solution. It is an ancient solution, a different path, equally valid, and perfectly adapted to the specific conditions of platypus life. The species has survived for tens of millions of years with this system, outlasting countless creatures that employed other reproductive strategies. It is not a living fossil, as it is sometimes called, because it has been evolving continuously throughout its long history. But it does carry within its biology whispers of the ancient world from which all mammals ultimately emerged. From the rivers of eastern Australia, we now travel south, across the Bass Strait, to the island state of Tasmania, where one of Australia's most dramatic and most misunderstood animals holds court over the dense temperate forests and open heathlands of that rugged island. The Tasmanian devil, Sarcophilus horizii, is the largest carnivorous marsupial alive on Earth today, a distinction it holds only because its larger relatives, including the thylacine or Tasmanian tiger, were driven to extinction in the 20th century by human persecution and habitat loss. The Tasmanian devil is, by any standard of honest description, a formidable animal. Compact and powerfully built, typically weighing between 13 and 26 pounds, it looks at first glance rather like a small, stocky, black bear. Its fur is predominantly black with irregular white patches on the chest and rump. Its head is large and broad, dominated by jaws of startling power. And it is those jaws that define the Tasmanian devil's ecological role and that have given this animal much of its fearsome reputation. The bite force of a Tasmanian devil, relative to its body size, is among the highest of any living mammal. When researchers measured the bite force of these animals relative to their body mass and compared the results across different species, the Tasmanian devil's performance was extraordinary. This bite force allows the devil to do something that few other predators can manage: to consume its prey completely, bones and all. A Tasmanian devil feeding on a carcass leaves virtually nothing behind. The heavy bones of a wallaby or a wombat, bones that would defeat the jaws of many larger predators, are crunched and consumed with apparent ease. The skull, the spine, the pelvis, all of it disappears into the devil's compact, efficient body, to be processed by a digestive system of impressive capacity. This ability to consume entire carcasses is not simply impressive. It is ecologically vital. Tasmanian devils function as the island's primary scavengers, cleaning up carcasses that would otherwise be vectors for disease transmission and fly strike in the humid temperate environment of Tasmania. They are nature's cleanup crew, and their efficiency in this role is unsurpassed by any other animal in their ecosystem. A group of Tasmanian devils can reduce a large wallaby carcass to nothing in a matter of hours, their feeding accompanied by the extraordinarily loud, aggressive vocalizations, the screeching, growling, and rasping that gave them their name and that can, on a dark Tasmanian night, send a cold chill down the spine of anyone unfamiliar with its source. Those aggressive feeding sounds, heard by the first European settlers in Tasmania before they had any clear idea of what animal was producing them, were terrifying enough to attach the word devil permanently to this species. The settlers heard screaming and snarling in the dark forests, and assumed the worst. What they were actually hearing was the competition and communication of a highly social animal at a feeding site, where multiple individuals of different social ranks negotiate access to a shared resource through a complex system of threat displays, vocalizations, and physical confrontation. Tasmanian devils are primarily nocturnal, spending their days in dens among rock crevices, in hollow logs, or in burrows dug by other animals. At night, they range widely across their territories, covering distances of up to 10 miles in a single night in search of food. While they are scavengers of considerable skill, devils also hunt live prey, particularly when carcasses are unavailable. Small wallabies, possums, lizards, snakes, birds, and invertebrates all fall prey to active hunting, and the devil's olfactory system, among the most sensitive of any marsupial, is capable of detecting the scent of a carcass from more than a mile away on a good wind. The reproductive biology of the Tasmanian devil involves an extraordinary race for survival at the very beginning of life. After a gestation period of around 3 weeks, the female gives birth to a litter of up to 40 tiny joeys, each one barely larger than a grain of rice. These tiny creatures must immediately begin a frantic crawl through the mother's fur to reach her pouch, propelling themselves with their tiny forelimbs with no assistance. The pouch contains only 4 nipples. The first 4 joeys to reach the pouch and attach to a nipple survive. The rest, the majority of the litter, perish. It is one of nature's most ruthless selection filters, ensuring from the very first moments of life that only the strongest and most vigorous offspring continue. Tragically, the Tasmanian devil today faces one of the most unusual and devastating threats ever to affect a wild mammal species. Devil facial tumor disease, a contagious cancer that is transmitted between individuals through biting, which is a normal behavior during feeding and mating, has swept through devil populations since its discovery in the 1990s. The disease causes large tumors to form around the face and mouth, eventually preventing affected animals from feeding, and leading to starvation and death, typically within 3 to 6 months of the first visible symptoms. Because devil populations show low genetic diversity in the immune genes responsible for tumor recognition, the animal's immune systems often fail to identify the tumor cells as foreign, allowing the disease to progress unchecked. The impact on devil populations has been catastrophic, with some regions losing more than 80% of their animals since the disease's emergence. But the species is not without hope. Conservation programs have established insurance populations of disease-free devils on offshore islands and in mainland facilities, and researchers have documented some encouraging signs of evolving resistance in certain wild populations. The devil story is not over. It is one of the most urgent and most carefully watched conservation dramas in the natural world, and the outcome remains genuinely uncertain. We move now from the dark forests of Tasmania northward, back to the mainland, to the eucalyptus woodlands and coastal forests of eastern Australia, where one of the most iconic of all Australian animals conducts its extraordinarily specialized and remarkably peaceful existence high in the tree canopy. The koala, Phascolarctos cinereus, has been enchanting human observers for as long as people have encountered it. Large, round, thickly furred, with enormous fluffy ears and a broad, flat nose, the koala has a stuffed toy appearance that makes it impossible to regard without a feeling of warmth and affection. But beneath that teddy bear exterior lies a biology of remarkable sophistication, evolved over millions of years to exploit one of the most challenging and toxic food sources imaginable. The koala is a specialist, and the object of its specialization is the eucalyptus tree. Australia is home to more than 700 species of eucalyptus, and eucalyptus forests and woodlands cover vast stretches of the continent. These trees are extraordinary plants in their own right, capable of growing in nutrient-poor soils, recovering rapidly from fire, and producing leaves year-round. But those leaves are also, by almost any nutritional standard, terrible food. They are extremely low in calories, low in protein, low in digestible carbohydrates. And they are toxic. The leaves of most eucalyptus species contain high concentrations of phenolic compounds and terpenes, chemicals that serve as chemical defenses against herbivory, and that would sicken or kill most other animals if consumed in quantity. The koala has evolved a comprehensive set of adaptations that allow it to safely exploit this challenging resource. The first line of defense is selectivity. Despite the abundance of eucalyptus species, a koala will typically only eat the leaves of a small number of species, sometimes as few as 3 or 4, even when other species are readily available. The leaves it selects tend to be those with lower toxin concentrations and higher water content. Individual koalas appear to develop specific preferences for particular species during the period when they are young and following their mother's foraging choices, suggesting that food selection behavior is at least partly learned rather than purely instinctive. The digestive system of the koala is heavily modified to deal with the toxins it inevitably ingests. The liver is enlarged and highly active in detoxifying phenolic compounds, processing them into forms that can be safely excreted. The cecum, a section of the large intestine, is extraordinarily long in the koala, reaching lengths of up to 8 feet. This extended cecum houses a community of specialized microorganisms, bacteria and other microbes, that assist in breaking down the complex plant chemicals in the eucalyptus leaves and in extracting whatever limited nutrition those leaves contain. Without this microbial community, a koala could not survive on its chosen diet. Joeys acquire their essential gut microbiome by eating a soft, specially produced form of their mother's feces during the transition from milk to solid food, a behavior that sounds unpleasant by human standards but that is an elegant and effective way of transmitting a vital microbial inheritance from one generation to the next. The caloric poverty of the eucalyptus leaf diet has profound behavioral consequences for the koala. Because the energy available from each meal is so limited, and because detoxifying plant chemicals is itself energetically expensive, the koala has evolved a lifestyle of radical energy conservation. An adult koala sleeps or rests for between 18 and 22 hours every day. It is one of the least active mammals on Earth during its resting periods, its metabolic rate dropping to levels that allow it to function on a diet that would be inadequate for virtually any other mammal of comparable size. When it does move, the koala's movements are slow and deliberate, designed to minimize energy expenditure. It travels between trees carefully, selecting routes that involve the least possible climbing and movement. This extraordinarily sedentary lifestyle, so perfectly matched to the koala's nutritional reality, also requires a specialized physical environment. The koala's hands and feet are adapted for a lifetime of gripping branches, with strong curved claws and, on the forefeet, an opposable digit that creates a powerful, secure grip on even smooth-barked eucalyptus trunks. The skin of the koala's palms and the soles of its feet has friction ridges so similar in appearance to human fingerprints that forensic scientists have occasionally found it difficult to distinguish between koala and human fingerprints at crime scenes, a biological coincidence that remains unexplained but suggests a common functional solution to the problem of maintaining grip on smooth surfaces. The koala's social life is organized around its eucalyptus forest habitat, with males maintaining territories that overlap with the ranges of multiple females. Males communicate primarily through deep, resonant bellowing calls that carry remarkable distances through the forest, advertising their presence and reproductive status. These calls, produced by a specialized sound-producing organ in the larynx that is unusually large relative to the animal's body size, are far deeper than one would expect from an animal of the koala's dimensions. The calls sound more like a belching rumble than anything one might expect from the koala's gentle appearance. During the breeding season, males become temporarily more active, ranging widely through their territories in search of receptive females. Females give birth to a single joey after a gestation of only around 35 days, and the tiny, undeveloped young makes its way to the pouch and attaches to a nipple. The joey remains in the pouch for around 6 to 7 months, then spends several additional months clinging to the mother's back and belly as it gradually gains independence. Leaving the eucalyptus forest behind, we return now to the desert, because the Australian outback is home to a wealth of reptilian life that deserves its own careful attention. The continent's reptile fauna is extraordinary in its diversity, and in the degree of specialization it displays. And among the most magnificent of all Australian reptiles is the largest, most dominant, and most commanding lizard on the continent, a creature that rules the desert with a combination of size, speed, intelligence, and predatory ferocity that makes it the undisputed apex reptilian predator of the Australian interior. The Perentie, Varanus giganteus, is Australia's largest monitor lizard and the fourth largest lizard species in the world. A fully grown Perentie can reach lengths of nearly 8 feet from snout to tail tip, and individuals of exceptional size may approach even greater lengths. Its body is powerfully built, covered in a beautifully patterned skin of cream and yellow spots and reticulations against a darker brown background, a coloration that provides excellent camouflage against the rocky, lichen-covered outback terrain where this animal is most commonly found. The tail, which accounts for more than half the animal's total length, is thick and muscular, a formidable weapon that can deliver a powerful blow to any perceived threat. The Perentie is a member of the Varanidie family, the monitor lizards, a group that includes the famous Komodo dragon of Indonesia and that is characterized throughout by high intelligence, active foraging behavior, and a physiology that is in many ways more similar to that of birds or mammals than to most other reptiles. Monitor lizards have high metabolic rates relative to other lizards, allowing them to sustain the kind of active, exploratory foraging behavior that less metabolically capable reptiles cannot maintain. They have well-developed brains, showing learning and problem-solving abilities in laboratory studies that exceed those of most other reptile groups. And they have a forked tongue connected to a highly developed vomeronasal organ, a chemical sensing structure in the roof of the mouth, that allows them to track prey by following scent trails with a precision that approaches the olfactory abilities of some mammals. The Perentie's hunting strategy reflects all of these capabilities. It is an active forager, spending much of its day moving through its territory, tongue flicking constantly to sample the chemical environment, investigating crevices and burrows, pursuing any prey that comes within reach. Its diet is broad and opportunistic, including lizards of all kinds, snakes including venomous species, small mammals, birds and their eggs, and carrion. When a Perentie encounters a large prey item, such as a young rabbit or a small wallaby, it seizes it in powerful jaws lined with sharp, recurved teeth, shaking and thrashing the prey to cause maximum damage and prevent escape. Recent research has revealed that monitor lizards, including the Perentie, possess a venom system, a discovery that overturned decades of scientific consensus about reptile venom. The venom is produced in glands in the lower jaw and enters wounds through grooves in the teeth. While the Perentie's venom is not particularly potent in its direct toxic effects, it does cause rapid blood pressure reduction and inhibits blood clotting, effects that would complicate the situation of an animal bitten and then pursued across the desert. Combined with the enormous physical damage that Perentie jaws can inflict, and the legendary ability of these lizards to outrun almost anything in their environment over short distances, the Perentie is a predator of genuine and well-deserved respect. Perenties are also remarkably accomplished climbers despite their size, scaling rocky outcrops with ease to access nesting birds or to seek refuge from the sun during the hottest parts of the day. Their thermoregulatory behavior is sophisticated, involving a complex daily schedule of sun exposure and shade-seeking that maintains their body temperature within the optimal range for physiological performance. In the extreme heat of an outback summer, a Perentie may emerge from its overnight refuge, bask briefly in the morning sun to raise its temperature to operating level, then shift to seeking shade during the middle of the day before resuming activity in the cooler late afternoon and evening. Females lay clutches of between 6 and 12 eggs in deep burrows or in termite mounds, where the constant biological activity of the termite colony maintains a relatively stable temperature and humidity level ideal for incubation. The young Perenties that emerge from these nests are miniature versions of the adults, immediately capable of feeding and fending for themselves, though they face a gauntlet of predators including large birds of prey and adult monitors of other species before reaching the size at which their own formidable attributes begin to provide real protection. Living alongside the great Perentie in the red deserts of Australia's interior is one of the most extraordinary small reptiles on Earth, a creature that has taken the challenge of surviving in an environment where water is almost perpetually scarce and solved it through one of the most elegant and unexpected biological innovations imaginable. The thorny devil, Molluc horridus, is a small lizard rarely exceeding 8 inches in length, covered from snout to tail tip in sharp conical spines of varying sizes, and sporting a false head, a spiny knob on the back of its neck that it presents to potential predators when threatened, tucking its real head between its forelegs in a gesture of protective deception. The thorny devil is a specialist of the highest order. Its entire diet consists of small black ants, a dietary restriction that might seem limiting but that actually reflects a calculated exploitation of one of the most abundant and reliable food resources in the desert environment. The thorny devil sits motionless beside ant trails, using its sticky tongue to pick up individual ants one at a time with metronomic precision. A single thorny devil may consume thousands of ants in a single feeding session, and the steady, predictable nature of ant trails means that once a productive location is identified, the lizard can return to it day after day and feed with minimal expenditure of energy. But it is the thorny devil's relationship with water, not its dietary specialization, that makes it truly one of the wonders of the Australian outback. Rainfall in the thorny devil's desert habitat may be absent for months at a time, and when it does fall, it may be so brief and so light that little of it penetrates the hard-baked soil surface. Yet the thorny devil is never dehydrated. It obtains water through a mechanism of such physical elegance that it reads almost like science fiction. The skin of the thorny devil is covered in an intricate network of microscopic channels. These channels, visible under magnification, run between and around the scales, forming a connected network that covers the animal's entire body surface. The channels are structured so that any moisture that contacts the skin, whether it be dew, light rain, or even moisture absorbed from damp sand is drawn automatically toward the corners of the mouth by capillary action. The moisture does not evaporate from the skin's surface. Instead, it travels through the channel network in a directional flow, driven purely by the physical properties of the channels themselves, until it reaches the mouth where the animal can swallow it. This system means that a thorny devil can stand in damp sand after a light shower and drink through its skin. It can walk through dew-wet grass in the early morning and absorb moisture as it moves. It can press itself into slightly moist soil and draw water from it. The amount of water obtained through any single such contact may be small, but over the course of a day, in an environment where every drop counts, the thorny devil's passive water collection system provides a consistent and reliable source of hydration that no other desert reptile has matched. The system is entirely passive, requiring no muscular effort, no behavioral specialization, no metabolic expenditure. It operates constantly whenever the skin is in contact with moisture, driven entirely by the physics of capillary action in precisely engineered channels. Engineers and materials scientists studying this system have been inspired by it in designing novel materials for passive fluid transport, a testament to the relevance of evolution's solutions to modern human technological challenges. No account of Australia's desert wildlife would be complete without addressing the animal that has earned, through purely biological achievement, the title of world's most venomous land snake. The inland taipan, Oxyurinus microlepidodus, lives in the remote, semi-arid black soil plains of central Australia, a harsh and largely inaccessible environment where it hunts the native rats and other small mammals that inhabit the deep cracks and burrows that form in the expansive cracking clays of these plains during drought. The inland taipan is not large by snake standards. A fully grown individual typically measures between 5 and 6 feet, though exceptional individuals may reach 8 feet. It is not dramatically colored. Its scales are rich, dark olive to brownish black in winter, fading to a lighter yellow-green in summer, a color change that is one of the most striking seasonal transformations in any reptile, driven by thermoregulatory needs rather than camouflage requirements. In winter, darker coloration absorbs solar radiation more efficiently, helping the snake warm up quickly in cool morning air. In summer, lighter coloration reflects more radiation, helping prevent overheating. What sets the inland taipan apart from all other land snakes is the extraordinary potency of its venom. Toxicologists who have measured the median lethal dose of various snake venoms have consistently found the inland taipan's venom to be the most toxic of any terrestrial snake. A single maximum venom yield from one bite contains enough toxin to kill more than 100,000 mice, or, by extrapolation, to be potentially lethal to hundreds of adult humans if left untreated. The venom acts through multiple mechanisms simultaneously, including neurotoxins that block nerve signal transmission at the junction between nerves and muscles, myotoxins that destroy muscle tissue, and anticoagulants that prevent blood from clotting. This combination of actions produces a syndrome of rapid and profound physiological collapse in prey animals. The evolution of this extraordinary venom potency is directly related to the inland taipan's prey. The native rats of the cracking clay plains, the primary targets of the inland taipan's hunting, are fast, agile, and capable of inflicting serious bites and scratches if a predator gives them any opportunity to do so. A snake that strikes and fails to incapacitate its prey immediately risks serious injury from the prey's defensive counterattack. The inland taipan's venom is so rapidly effective that prey animals are typically immobilized within seconds of being struck, drastically reducing the risk of retaliatory injury to the snake. The extraordinary potency of the venom is, in essence, an evolutionary arms race solution, the snake's response to the specific defensive capabilities and behaviors of its prey species. Despite its fearsome venom, the inland taipan is by temperament a retiring and non-aggressive animal. It occupies one of the most remote and inhospitable regions of Australia, and human encounters with wild inland taipans are genuinely rare. The species has a calm, deliberate demeanor that contrasts sharply with the explosive aggressiveness of some other highly venomous snake species. When encountered, it typically attempts to escape rather than confront, and bites to humans are extremely uncommon. There are no recorded human fatalities from inland taipan bites, and the cases that have occurred have all been successfully treated with antivenom. The inland taipan is a perfect illustration of a principle that runs through much of Australian wildlife. The most extreme biological adaptations are not expressions of malevolence or aggression. They are precise, elegant solutions to the specific survival challenges posed by a specific environment. The inland taipan's venom is extraordinary not because the snake is dangerous to humans, but because it has been shaped over millions of years to solve a very specific problem with maximum efficiency. We turn now to the ancient rainforests of northeastern Australia, to the wet tropics of far north Queensland, where the dense green canopy of one of the oldest rainforest systems on Earth shelters an animal of extraordinary dimensions and extraordinary ecological importance. The southern cassowary, Casuarius casuarius, is the third largest bird on Earth by height, trailing only the ostrich and the emu, and is arguably the most architecturally dramatic bird in Australia. An adult female, which in cassowaries is larger than the male, can stand nearly 6 feet tall and weigh up to 150 pounds. She is clothed in drooping, hair-like black feathers that hang from a powerfully muscled body. Her neck is bare and brilliantly colored, electric blue at the base transitioning to rich red at the back, adorned with fleshy red wattles that hang like pendants at the throat. And crowning her head is the casque, a tall, helmet-like structure of hardened keratin and bone, its function still not entirely understood by scientists but possibly involved in low-frequency sound communication, in pushing through dense vegetation, or in display. The cassowary's feet are among the most formidable natural weapons possessed by any bird. The inner toe of each foot bears a long, straight, dagger-like claw that can reach 5 inches in length. A cassowary that feels threatened can deliver powerful kicks capable of disemboweling larger animals, and the species is rightly regarded with caution in the wild. But the cassowary's biological significance extends far beyond its capacity for self-defense. In the rainforest ecosystem, the cassowary plays a role of such importance that its presence or absence can fundamentally alter the composition and structure of the forest itself. The cassowary is a frugivore, feeding primarily on fallen fruit that it finds on the rainforest floor. Its digestive system is capable of processing the large fruits of many rainforest trees, extracting the nutritious pulp and passing the seeds through its gut intact and deposited in a pile of nutrient-rich feces some distance from the parent tree. And it is this seed dispersal service that makes the cassowary indispensable. Of the more than 100 plant species in the wet tropics rainforest that produce large fruits, a significant proportion rely almost exclusively on the cassowary for their seed dispersal. Many of these plants produce fruits too large to be swallowed by any other forest animal. Without the cassowary to eat them and carry the seeds away, these plants would simply drop their seeds at the base of the parent tree, where competition from the parent and from other seedlings would mean that very few would survive to become mature trees. The loss of the cassowary from a section of rainforest through habitat destruction or any other cause would therefore set in motion a cascade of changes in forest composition that would unfold over decades and centuries, as the large-fruited trees that depend on cassowaries for reproduction gradually declined and disappeared from the system. The cassowary is what ecologists call an ecosystem engineer, a species whose activities physically create and maintain the habitat upon which many other species depend. Its conservation is not merely a matter of preserving a single spectacular bird. It is a matter of maintaining the integrity of an entire ancient forest system. Cassowary conservation in Australia is challenging because the species occupies a relatively small range in far north Queensland and faces a combination of threats including habitat loss and fragmentation, vehicle strikes on roads that pass through the forest, and predation of eggs and chicks by feral pigs. The population of southern cassowaries in Australia is estimated at only a few thousand individuals, making it a genuinely vulnerable species. The reproductive behavior of the cassowary reverses the typical gender roles found in most bird species. After mating, the female lays a clutch of 3 to 5 large, green eggs in a shallow nest on the forest floor and then departs, taking no further interest in the reproductive process. It is the male who incubates the eggs for approximately 50 days, sitting on the nest through the heat of the day and the darkness of the night, barely eating, barely moving, turning the eggs regularly to ensure even temperature distribution. When the chicks hatch, They are beautiful, striped in brown and buff, and they remain with the father for up to 16 months, following him through the forest as he teaches them, through example, which fruits to eat and how to navigate the complex three-dimensional environment of the rainforest interior. From the rainforest, our story moves north to the rivers, floodplains, and coastal wetlands of tropical Australia, where the waters are ruled by one of the most ancient lineages of large predators still living on Earth. The crocodilians have been present on this planet for more than 200 million years, their basic body plan so perfectly matched to the demands of a semi-aquatic ambush predator's lifestyle that the passage of geological epochs, the extinction events that wiped out the dinosaurs and reshuffled the biological deck of the world, the rise and fall of entire faunas, none of it has required them to change substantially. What hunts in the rivers of Australia today is recognizably similar, in its fundamental design and biology, to what hunted in the swamps of the Triassic. Australia is home to two species of crocodilian. The freshwater crocodile, Crocodilus johnstonii, is a smaller and considerably less dangerous species, reaching typical adult lengths of around 6 to 8 feet, that is found in rivers, lakes, and billabongs across much of northern Australia. It feeds primarily on fish, frogs, and small animals, and while it can inflict serious bites if cornered or molested, it does not view humans as prey, and attacks on people are extremely rare. The saltwater crocodile, Crocodilus porosus, known colloquially and with good reason as the salty, is a different matter entirely. It is the largest living reptile on Earth, and one of the most formidable predators alive anywhere on the planet. Adult males regularly exceed 16 feet in total length, and the largest confirmed individuals have approached 23 feet, with body weights of more than 2,000 pounds. At these dimensions, the saltwater crocodile becomes capable of prey items of virtually any size, and it ranges far beyond its nominal name suggests, occurring not only in coastal saltwater habitats, but throughout the freshwater river systems, billabongs, and swamps of northern Australia. Traveling overland between water bodies during the wet season and making oceanic crossings between islands that demonstrate impressive navigational ability. The saltwater crocodile is an ambush predator of extraordinary patience and precision. Its hunting strategy is built around the intersection of two facts. Virtually every large animal in its environment must visit water regularly to drink, and the crocodile can wait, absolutely motionless, for extraordinary periods of time. The animal's metabolism is so efficiently tuned that a large adult can survive for many months without feeding, drawing on fat reserves accumulated during successful hunting periods. This means there is no cost to waiting. A crocodile that positions itself in a favored location near a drinking site can lie beneath the surface with only its eyes and nostrils exposed, indistinguishable from a floating log, for hours, days, even longer, until a suitable prey animal presents itself. When the moment comes, the strike is among the fastest movements executed by any large animal on Earth. The crocodile explodes from the water with a force that can propel its entire body completely clear of the surface, seizing prey in jaws that exert a bite force of several thousand pounds per square inch, the highest recorded for any living animal. The prey is dragged into the water, where the crocodile uses a technique known as the death roll, spinning its body rapidly around its long axis while maintaining its grip on the prey, to tear large chunks of flesh from the body or to drown large animals that cannot be immediately subdued. The intelligence of the saltwater crocodile is frequently underestimated. These animals learn from experience, modify their hunting strategies based on the behavior of specific prey species or individuals, and demonstrate long-term memory of productive hunting locations and seasonal prey availability. Researchers studying crocodile populations in northern Australia have documented complex social hierarchies, sophisticated territorial behaviors, and communication through a range of visual, acoustic, and vibrational signals. During the breeding season, which occurs in the dry season months, the male's activities include elaborate courtship displays and serious territorial battles with rival males, battles that can cause significant injuries and that establish the social hierarchy governing access to females and prime territories. Female saltwater crocodiles are attentive and surprisingly devoted mothers by reptile standards. Each female constructs a large mound nest of vegetation and soil in which she lays between 40 and 60 eggs. She guards the nest site aggressively throughout the incubation period of around 90 days, rarely leaving, deterring potential predators with threat displays and genuine attacks. When the eggs are close to hatching, the young crocodiles begin calling from inside their shells, producing yelping sounds that signal the mother to open the nest. She carefully excavates the nest mound with her powerful limbs and picks up the hatching young in her mouth, gently carrying them to the water's edge. For several months after hatching, the female continues to guard her offspring, shepherding them away from danger and providing a protected environment during the most vulnerable period of their lives. The recovery of saltwater crocodile populations in Australia following their protection from hunting in the 1970s is one of the great success stories of wildlife conservation. Before protection, hunting for their valuable hides had reduced crocodile populations to critically low levels across much of their range. Within decades of receiving legal protection, numbers rebounded dramatically, and today the saltwater crocodile is once again abundant across much of northern Australia. This recovery has created its own complex set of management challenges, as crocodile populations living in close proximity to human communities require careful monitoring. But it also represents a powerful demonstration of nature's resilience when the pressure of unsustainable exploitation is removed. We move now from the waterways to the underground, because some of Australia's most remarkable animals have chosen to seek their survival not at the surface of the land but beneath it. Digging, burrowing, and tunneling represent some of the most energetically demanding forms of locomotion in the animal kingdom, requiring specialized skeletal structures, powerful musculature, and extraordinary sensory systems for navigating in total darkness. And yet Australia has produced multiple species that have embraced the underground environment with extraordinary success. The common wombat, Bombatus ursinus, is the most familiar of Australia's champion diggers. A large, barrel-shaped marsupial that can weigh up to 80 pounds in large individuals, the wombat is built like a living excavation machine. Its forelimbs are short and enormously powerful, equipped with broad, flattened claws designed for scraping and shoveling. Its skull is heavy and robust, reinforced for pushing through compacted soil. Its legs are short relative to its body, keeping its center of gravity low and providing excellent traction when pushing against the resistance of an earth wall. And its teeth, particularly the large, chisel-like incisors, continue growing throughout the animal's life, compensating for the wear that comes from a lifetime of gnawing through roots and compacted soil. A wombat's burrow system is a remarkable piece of engineering. The main burrow may extend 30 feet or more into the hillside or plain, with multiple side branches, secondary entrances, and resting chambers. The digging of such a system represents an enormous investment of time and energy, but the returns are equally significant. The burrow maintains a relatively constant temperature and humidity regardless of surface conditions, providing refuge from the extremes of both summer heat and winter cold. It provides protection from predators, and the narrow burrow entrance is easy to defend, with the wombat's heavily reinforced rear end serving as a literal shield that blocks the entrance and can deliver crushing blows to any predator attempting to follow it underground. The wombat's digestive system is one of the most efficient in the marsupial world. The process of moving food through the wombat's digestive tract takes around 100 to 150 hours, compared to around 24 hours in most comparable mammals. This extraordinarily slow digestion allows the wombat to extract the maximum possible nutrition from the low-quality grasses and roots that make up most of its diet, an essential adaptation in environments where food quality and availability can be poor. The wombat also produces the world's only known cubic feces, a biological curiosity that has attracted genuine scientific interest. The production of these distinctive cube-shaped droppings is achieved through a mechanism in the final section of the large intestine where uneven elastic properties of the intestinal wall create a corrugated drying effect that molds the feces into their characteristic form. These cubic droppings do not roll away on the uneven terrain where wombats deposit them, meaning that they remain precisely where the animal left them to serve their function as scent markers, communicating the wombat's presence and territorial status to other individuals. Far less familiar than the wombat, and far more extreme in its subterranean lifestyle, is the marsupial mole, Notarichtes typhlops. This remarkable creature is not related to the true moles of the northern hemisphere. It is instead an extraordinary example of convergent evolution, the process by which completely unrelated animals, faced with similar environmental challenges, independently evolve strikingly similar solutions. The marsupial mole has evolved the same basic body plan as the true moles of Europe and North America, compact and cylindrical, with powerful forelimbs equipped with digging claws, vestigial eyes covered by skin, no visible external ears, and a velvety, soft fur that lies equally flat in any direction to facilitate movement through soil. Yet it is a marsupial, carrying its tiny young in a backward-facing pouch that prevents soil from entering during digging. The marsupial mole does not dig permanent tunnels. It swims through the sandy desert soils of central Australia, leaving a temporary tunnel behind it that immediately collapses as it passes. This makes studying the animal's behavior in the wild extraordinarily difficult, as there is no burrow to excavate, no regular route to monitor. Marsupial moles spend almost their entire lives underground, surfacing only occasionally after rain, presumably to forage for the invertebrates and lizard eggs that constitute their diet. Their eyes are completely non-functional, covered by a shield of skin, vestiges of organs that ancestral populations once used but that underground life has rendered entirely redundant. Their sense of touch, mediated through the sensitive skin of the forelegs and snout, is presumably their primary means of navigating and hunting in their lightless environment. The rivers, coastlines, and open water surrounding Australia harbor an equally extraordinary array of specialized wildlife, and we now turn our attention to some of these remarkable creatures. The Australian pelican, Pelecanus conspicuatus, is among the most instantly recognizable waterbirds in the world, distinguished by the largest bill of any bird species on Earth, a magnificent, pouched structure that can reach lengths of nearly 20 inches. This bill is not merely for catching fish, though it is highly effective at that, but is also an important thermoregulatory organ, the highly vascularized skin of the pouch radiating excess heat when the pelican flutters it in the sun. Australian pelicans are highly social birds, often feeding cooperatively in groups that herd fish into shallow water before scooping them up in coordinated dips of their capacious bills. Their breeding colonies can number in the thousands, and the social dynamics of these colonies, the competition for nesting sites, the pair bonding rituals, the shared care of eggs and chicks, present a complex and fascinating social world that researchers have studied for decades without exhausting its complexity. The short-beaked echidna, Tachyglossus aculeatus, is one of the world's 4 remaining monotreme species and the only one besides the platypus to live in Australia. Like the platypus, the echidna lays a single leathery egg, placing it directly into its pouch where the young, known as a puggle, hatches and remains for several months, suckling milk that seeps through patches of specialized skin. The echidna's body is covered in a combination of fur and sharp spines of modified keratin, which serve as its primary defense against predators. When threatened, it rolls into a tight ball, presenting a sphere of outward-pointing spines to any potential attacker, or wedges itself into a crevice with its spines locked outward, becoming virtually impossible to dislodge. The echidna's feeding is accomplished through a long, tubular snout and an extremely long, sticky tongue that can be extended rapidly to capture ants, termites, and other invertebrates from their nests and galleries. Echidnas have no teeth and swallow their food whole, relying on a muscular part of their stomach to grind the insects against hardened plates. Their forelimbs are extremely powerful, capable of breaking open concrete-hard termite mounds and digging with a speed and force that seems almost incongruent with the animal's placid appearance. In the warm, shallow coastal and reef waters of Australia's northern and eastern coasts, a creature of deadly beauty hunts among the coral and rock, its vivid coloration serving as an unambiguous warning to any organism intelligent enough to recognize it. The blue-ringed octopus, of which several species occur in Australian waters, is among the most venomous marine animals in the world. A small animal, typically no larger than a tennis ball when contracted, the blue-ringed octopus normally displays a muted pattern of brown and yellow coloration that provides effective camouflage against the rocky bottom. But when threatened or agitated, it undergoes a transformation of startling speed, the iridescent blue rings that give it its name flashing to brilliant life across its body, pulsing with electric intensity in a display that communicates with absolute clarity to any observer, "Approach me and you will die." The venom of the blue-ringed octopus is among the most potent in the ocean, containing tetrodotoxin, the same extraordinarily powerful neurotoxin found in pufferfish, produced by bacteria that live in symbiosis with the octopus. The toxin blocks the sodium channels in nerve cell membranes, preventing nerve impulses from being generated, rapidly causing paralysis of muscles including those controlling breathing. A person bitten by a blue-ringed octopus and not given immediate respiratory support can die from asphyxiation within minutes. There is no antivenom. Survival depends entirely on rapid application of artificial respiration maintained until the toxin is cleared from the body, a process that may take many hours. The green sea turtle, Chelonia mites, represents one of the most ancient lineages of reptiles still alive, a creature whose ancestors navigated the warm seas of the Cretaceous alongside dinosaurs. Australian waters host significant green sea turtle populations, with major nesting sites along the Queensland coast, including the famous Rain Island, where tens of thousands of females return each nesting season to lay their eggs on the beach where they themselves were born, navigating thousands of miles of open ocean with navigational precision that still challenges scientific explanation. The box jellyfish, Chironix fleckeri, is the most venomous marine creature on Earth, and Australian waters, particularly those of the tropical north, are home to the most dangerous species. A box jellyfish's venom is so rapidly effective that it can cause cardiovascular collapse and death in an adult human within minutes. The jellyfish possesses true eyes with lenses, retinas, and irises capable of forming images, a remarkable capability for an animal without a centralized brain, and it uses these eyes to actively navigate its environment. And in the warm, seagrass-rich shallows of tropical Australia, the dugong grazes with a bovine placidity that has earned it the common name sea cow. A large marine mammal, closely related to the manatees of other oceans, the dugong is the only surviving member of its genus, and one of only 4 living sirenian species. Its feeding on seagrass beds makes it a keystone grazer in coastal marine ecosystems, its grazing patterns influencing the composition and structure of the seagrass communities on which countless other species depend for food and habitat. And so we have journeyed across the extraordinary living tapestry of wild Australia, from the red heart of the desert to the blue depths of the coral sea, encountering along the way creatures of such remarkable diversity and such breathtaking biological innovation that the mind struggles to hold them all simultaneously. We have run with red kangaroos across the shimmering outback plains. We have watched dingoes coordinate their hunts with pack intelligence refined over thousands of years. We have smiled at quokkas on sun-warmed rocky shores, marveled at the platypus navigating darkness by electrical sense, heard the terrifying shriek of Tasmanian devils around a midnight carcass, sat in eucalyptus-scented air watching a koala eat its way through another toxic meal with slow and perfect contentment, stood in the trembling shadow of a Perentie as it scans the desert with its forked tongue, watched a thorny devil drink through its skin from dew-wet grass, felt the hair rise on our arms contemplating the inland Taipan's invisible perfection, and looked up into the ancient rainforest canopy to see a cassowary move through the undergrowth like a piece of the living forest itself. We have heard the ancient percussion of the earth and the thunder of crocodile jaws closing, felt the vibration of powerful digging in the tunnels and burrows beneath our feet, watched pelicans wheel against the blue sky, echidnas snuffle through leaf litter, blue-ringed octopuses pulse their deadly warning, sea turtles rise to breathe in moonlit waters, dugongs graze in underwater meadows, and box jellyfish trail their invisible, lethal ribbons through the warm tropical sea. This is Australia. Ancient beyond easy comprehension. Extreme in its environments and its demands. Ingenious in its solutions. And more alive, more fundamentally, irreducibly alive, than almost any place on Earth. And this is only the beginning. In Part 2 of Wild Australia, Secrets of an Ancient Continent, we will journey deeper into the story of this remarkable land, exploring the great cycles of fire and flood that govern life in the Australian interior, witnessing the dramatic resurrection of life that follows the rains, and confronting the urgent conservation challenges that threaten to unravel millions of years of evolution in a fraction of a heartbeat of geological time. The story of Australia is a story of survival against impossible odds. It is a story that is still being written. And it deserves our closest, most devoted attention. Stay with us. Because the most extraordinary chapters are yet to come. There is a moment, somewhere in the vast red interior of Australia, when the world holds its breath. The sky has been building for days, towering columns of cloud rising from the northern horizon like the smoke of 1,000 fires, their undersides darkening from white to gray to a bruised and ominous purple that seems to press down upon the land with a physical weight. The air smells different, charged with electricity and the distant ghost of moisture, a smell that the animals of the Outback have not encountered for months, perhaps for years. The kangaroos raise their heads from the dry, cracked earth. The dingoes sit and face the coming weather with their great amber eyes open wide. The lizards pause in their endless foraging and go still. Even the insects seem to quiet. And then, with a crack of thunder that rolls across 300 miles of empty plain and a first fat drop of rain that hits the red dust and explodes into a tiny crater of dark moisture, the silence breaks, and Australia begins to live again. Welcome back to Wild Australia, Secrets of an Ancient Continent. In Part 1, we traveled across this extraordinary land and met its cast of biological marvels, from the bounding red kangaroo to the electric-sensing platypus, from the world's most venomous land snake to the ancient, cast southern cassowary. We explored millions of years of evolutionary isolation and the astonishing diversity it has produced. Now, in Part 2, we go deeper. We follow the great cycles of fire and flood that are the true heartbeat of the Australian continent, the primal rhythms that drive everything, that kill and create in equal measure, that have shaped every animal and every plant on this land into what they are today. We explored the relationships between species, the hidden webs of dependency and competition that hold ecosystems together. We look at the remarkable world of Australia's birds, its insects, its fungi, its ancient plants. And we face, honestly and directly, the conservation challenges that threaten to unravel millions of years of evolution within the span of a single human lifetime. Please let us know in the comments where you are watching this documentary, and what time you are watching it. And be sure to subscribe to the channel for future videos. Now let us continue the journey. To understand Australian wildlife in its full complexity and beauty, you must understand fire. Not fear it, not simply acknowledge it as a hazard and a tragedy, but truly understand it as the continent's most fundamental ecological force, as essential to the functioning of Australian ecosystems as sunlight and rain, as ancient in its relationship with the Australian biosphere as the continent itself. Fire and Australia have been partners for so long, have been so deeply intertwined in the evolution of the continent's plants and animals, that to remove fire from the equation would be to destroy the very system you were trying to protect. The story of fire in Australia begins with the continent's climate, specifically with the extraordinary dryness that characterizes such a large proportion of the continent's interior. Australia is the driest inhabited continent on Earth. Its interior receives rainfall so irregularly, so unpredictably, that planning or predicting based on any kind of regular seasonal cycle is impossible. Years of drought are followed by years of flooding rain, followed by more drought, with no reliable pattern that animals or plants or humans can depend upon. During the drought years, vegetation dries to a crisp brittleness that makes it among the most flammable organic material on the planet. The eucalyptus forests, which cover such a vast proportion of the continent, are particularly combustible. Eucalyptus leaves contain high concentrations of volatile oils, the same terpene compounds that give eucalyptus its characteristic sharp, medicinal smell, and these oils are extraordinarily flammable. A eucalyptus forest on a hot, dry, windy day is, in effect, a landscape preloaded with fuel. Lightning strikes provide the ignition. During the dramatic electrical storms that accompany the leading edge of seasonal weather systems, lightning can strike the same dry landscape dozens of times in a single afternoon, and each strike carries the potential to ignite the tinder-dry vegetation. And once ignited, an Australian bushfire in the right conditions moves with a speed and ferocity that must be witnessed to be fully appreciated. Fire fronts can travel at speeds exceeding 60 miles per hour in strong winds. They can jump across rivers, highways, fire breaks, and any other barrier that human engineering might devise. They can create their own weather systems, generating pyrocumulonimbus clouds, essentially thunderstorms born from the heat of the fire itself, that can drop burning embers miles ahead of the main front, starting new ignitions and effectively surrounding areas that might otherwise have been spared. In the face of this, Australia's wildlife does not simply endure fire. It has evolved to exploit it, to live within the fire cycle as naturally and as completely as a fish lives within water. And the complexity of these fire adaptations is one of the most extraordinary chapters in the entire story of Australian natural history. The plants lead the way, and the strategies they have developed over millions of years of coexistence with fire are nothing short of astonishing. The eucalyptus tree, already so central to our story in the context of the koala, displays perhaps the most impressive fire survival adaptations of any plant genus on Earth. After a fire sweeps through a eucalyptus forest, destroying the canopy and apparently reducing the trees to charred poles, the recovery begins with almost indecent haste. Within days, sometimes within hours of the fire passing, new growth begins erupting from beneath the bark of the surviving trunks. These epicormic shoots, as they are called, emerge from dormant buds that lie protected beneath the thick, insulating bark of the eucalyptus trunk, buds that have been waiting, sometimes for decades, for exactly this moment of canopy removal and increased light availability. The speed and abundance of this epicormic shooting is breathtaking. A eucalyptus trunk that appears to be completely dead, its bark blackened, its canopy gone, its surface still warm to the touch from the fire that passed through, will within 2 weeks be flushed green with hundreds of new shoots erupting simultaneously from its entire surface. Within months, the forest is recovering. Within a few years, it may be difficult to detect from a distance that any fire passed through at all, though an ecologist walking through the regenerating forest would see the signs of fire and recovery written in the structure and composition of the vegetation at every step. Many eucalyptus species also maintain lignotubers, large, woody swellings at the base of the trunk and at the root crown, which contain enormous reserves of dormant buds and stored carbohydrates. Even if a fire kills the entire above-ground portion of the tree, the lignotuber survives below the soil surface, protected by the insulating properties of the earth, and from it the tree regrows, using its stored energy reserves to produce new shoots before it has any photosynthetic leaf area to generate fresh energy. This means that a eucalyptus plant is in some sense functionally immortal. Its above-ground portions may be destroyed repeatedly by fire, but as long as the lignotuber survives, the plant continues. Some lignotubers have been estimated to be thousands of years old, representing an individual plant organism that has been cycling through destruction and regeneration since long before European settlement of the continent. The flowering that follows fire in many Australian plant species is another dimension of fire ecology that reveals the deep intimacy between this continent's flora and the flames that have shaped it. Certain species of grass tree, those extraordinary plants with their tufts of thin leaves atop thick, fire-blackened trunks that are such an iconic feature of Australian heathland, flower almost exclusively after fire. The heat and chemical signals produced by the passing fire seem to trigger their flowering response, and within weeks of a fire, the blackened landscape is punctuated by the tall, cream-colored flower spikes of grass trees thrusting upward from the ash. The nectar these flowers produce attracts insects, birds, and small mammals in extraordinary abundance, creating a pulse of biological productivity in the post-fire landscape that provides critical resources for a wide range of species during the period of vegetation regeneration. Banksias, those remarkable flowering shrubs and trees whose dramatic, torch-like flower heads are among the most visually distinctive features of Australian heathland, have evolved a range of fire response strategies that vary between species and even between individual plants depending on their location and the local fire regime. Some Banksias store their seeds in tough, woody follicles on their branches, follicles that remain sealed for years until the heat of a fire triggers them to open, releasing their seeds onto a freshly cleared landscape that is rich in nutrients from the ash and has had its competing vegetation removed. Other Banksias rely on lignotubers for vegetative resprouting. Still others depend on a rapid regeneration from seed, their seedlings racing to establish themselves in the window of reduced competition that follows fire before the vegetation closes in again. This diversity of fire response strategies within a single plant genus reflects the diversity of fire regimes that different parts of Australia experience. An area that burns frequently, every few years, selects for plants that can resprout rapidly from protected growing points after each fire. An area that burns rarely but intensely selects for plants that can survive decades of fuel accumulation and then withstand the fierce, hot fires that result. And an area with an intermediate fire regime may support a mixture of both strategies, producing the extraordinary floral diversity that makes places like the southwestern corner of Australia, with its thousands of endemic plant species, among the most botanically rich regions on Earth. The animals of Australia have not stood passively on the sidelines of this evolutionary conversation between fire and plants. They too have been shaped by millions of years of fire, and they participate actively in the fire cycle in ways both direct and indirect. The most immediate response of most animals to an approaching fire is, naturally, to flee. Large, fast-moving animals such as kangaroos, emus, and many species of lizards simply move away from the advancing fire front, traveling as fast as they can in a direction that takes them away from the smoke and heat. This flight can take individuals many miles from their normal home ranges, and the gathering of displaced animals in refugia beyond the fire perimeter, areas that escaped burning due to topography, moisture, or simply the unpredictable behavior of fire in complex terrain, creates temporary concentrations of wildlife of remarkable density. But not all animals flee. Some small mammals, lizards, frogs, and invertebrates seek refuge in their burrows or in the soil itself, relying on the insulating properties of the earth to protect them from the passing fire. The temperature inside a burrow, even a few inches below the surface, may be only marginally elevated during a fast-moving fire, while the surface temperature above reaches hundreds of degrees. Many species have evolved to recognize the signs of approaching fire and retreat to underground refuges in time to survive. Others, particularly soil-dwelling insects and their larvae, survive by remaining in the soil throughout the fire season as a normal part of their life cycle. And then there are the animals that follow fire, and that have evolved specific behaviors to exploit the ecological opportunities that the post-fire landscape presents. Perhaps the most dramatic of these are the fire-following birds, a guild of species that has been documented in Australian science with increasing fascination in recent decades. The black kite, a common and widespread raptor across much of Australia, has long been known to gather at the edges of fires, catching small animals fleeing the flames. But more remarkably, black kites and several other raptor species have been documented actively transporting burning sticks from fire fronts to unburned vegetation, apparently to start new fires and drive additional prey from cover. This fire-carrying behavior, which has been reported by Indigenous Australians for thousands of years and is documented in their oral traditions and cultural knowledge, has only recently received serious scientific attention, and the studies that have examined it have confirmed that the behavior is real and that it does result in the spread of fire beyond the natural boundaries set by wind and terrain. It represents a level of deliberate tool use and behavioral sophistication in wild birds that challenges our assumptions about the cognitive abilities of non-human animals, and it adds yet another layer of complexity to the already intricate relationship between fire and Australian wildlife. Of all the post-fire ecological processes in Australia, none is more dramatic, none more visually spectacular, and none more biologically important than the return of water. The rains that follow the dry season or break a prolonged drought transform the Australian landscape with a speed and completeness that must be experienced to be fully believed. What was, days before, a cracked and dusty plain of bare red soil and desiccated plant skeletons becomes, within hours of the first significant rainfall, something entirely different. The transformation is so rapid, so total, so joyful in its biological exuberance, that it seems less like a weather event and more like a resurrection. The mechanism of this transformation begins at the smallest scale, in the soil itself. Australian desert soils, though they appear lifeless, contain a wealth of biological material in a state of suspended animation. Seeds of dozens of plant species lie dormant in the soil, some of them capable of remaining viable for many years, waiting for the specific combination of moisture and temperature that signals a favorable germination window. Spores of mosses, fungi, and algae wait in similar suspended states. Eggs of crustaceans, resting stages of various invertebrates, dormant bacteria and other microorganisms, all of these wait in the soil, at biological zero, consuming no energy, existing in a state between life and death, for the signal that water provides. When the rain comes and penetrates the soil, the response at this microscopic level is immediate and explosive. Within hours, bacteria and algae begin dividing. Within days, moss spores germinate and begin producing the first green threads of new growth. Within a week, the first cotyledons of annual wildflowers push through the soil surface, and the desert floor begins to blush green with the first suggestion of the carpet that will soon cover it completely. The speed of these responses reflects millions of years of selection for the ability to exploit the brief windows of moisture that desert environments provide, windows that may be weeks or months long at best, and that must be used with maximum efficiency. Within 2 to 3 weeks of a significant rain event, the transformation of the landscape is already extraordinary. The bare red plains have become green meadows. Wildflowers in an astonishing diversity of colors and forms bloom in such profusion that the desert floor is painted in sheets of yellow, purple, white, and pink that extend to the horizon. The speed of their flowering reflects the extreme selection pressure of the desert environment: germinate fast, grow fast, flower fast, set seed fast, and die before the moisture runs out and the brutal heat returns. These ephemeral annual plants have life cycles that can compress an entire year's worth of biological activity into a few weeks, completing germination, growth, flowering, pollination, seed set, and death before the surface soil has time to dry again. The insects respond to this floral abundance with equal speed. Within days of the wildflowers opening, bees, beetles, butterflies, moths, flies, and wasps appear in numbers that seem impossible given the apparent emptiness of the desert just weeks before. Many of these insects also overwinter as dormant eggs, pupae, or dormant adults in protected locations, emerging in response to the same warmth and moisture signals that trigger plant germination. They feed on the nectar and pollen of the ephemeral flowers, themselves mate and reproduce with the same urgency as the plants, and must complete their reproductive cycles before the flowers disappear. The aquatic invertebrates provide perhaps the most dramatic example of desert resurrection. In the temporary lakes and flooded plains that form after heavy rains, water that may remain for only weeks or months, populations of fairy shrimps, shield shrimps, clam shrimps, and copepods appear within hours of the water's arrival. These creatures spent the intervening dry period as drought-resistant eggs buried in the dry lake bed sediments, eggs that can survive desiccation, extreme heat, freezing temperatures, and the passage of many years without losing their viability. When water returns, the eggs hatch almost simultaneously, and within a day or two, the newly formed lake is teeming with billions of tiny crustaceans, feeding on the bacteria and algae that bloomed even faster, growing and reproducing at maximum speed, racing to complete their life cycles and produce the next generation of drought-resistant eggs before the water disappears again. This biological explosion in the temporary water bodies attracts waterbirds from across the continent in one of the great wildlife spectacles of the natural world. Australian waterbirds, including pelicans, ducks, ibis, spoonbills, herons, egrets, cormorants, and many others, have evolved a nomadic lifestyle that is unique among the world's waterbird communities. Rather than maintaining fixed breeding territories that they return to each year, most Australian waterbirds track rainfall across the continent, moving hundreds or thousands of miles in response to the creation of temporary wetlands, and breeding wherever food and water are simultaneously abundant. The timing of these breeding events is astonishing. A waterbird colony that did not exist 2 weeks ago may, within a month of rain filling a previously dry lake, contain tens of thousands of breeding pairs, the air above the lake white with birds, the surrounding vegetation laden with nests and chicks, the noise of the colony audible for miles. These enormous, temporary breeding aggregations produce astonishing numbers of young birds, exploiting the brief window of productivity that the temporary wetland provides before it dries again. When the lake recedes, the colony disperses, the adults and their now-fledged young scattering across the continent in search of the next rainfall event. The emergence of frogs from their dry season refuges is another of the transformation's defining moments. Australia has approximately 240 species of frogs, a remarkable diversity for a continent with such extensive arid and semi-arid zones, and many of these species have evolved extraordinary strategies for surviving the long dry periods between breeding opportunities. The most spectacular of these are the water-holding frogs, members of the genus Cyclorana, which spend the dry season cocooned inside a multi-layered skin shed from their own bodies, buried deep in the soil, their metabolism reduced to the absolute minimum necessary to maintain life. A water-holding frog buried in dry desert soil exists at the very boundary of biological activity. Its heart beats only occasionally. Its breathing slows to a rate that, in any other context, would indicate death. Its body temperature tracks the soil temperature passively, rising with the day's heat and falling with the night's cold, as no energy is being generated internally to maintain a constant temperature. And inside its body, stored within its bladder and its lymph spaces, are reserves of water accumulated during the previous wet season, enough to sustain the animal through months or even years of dormancy. Indigenous Australians, who possessed profound knowledge of their environment's resources, knew of these water-holding frogs and occasionally excavated them from the soil to use the stored water as a survival resource. When rain falls and penetrates deep enough into the soil to reach the buried frogs, the response is immediate. The vibration of raindrops on the soil surface, the sudden change in soil moisture and temperature, and perhaps chemical signals dissolved in the percolating water all act as triggers that bring the frog back from its near-death state with remarkable speed. Within hours of the first rain, frogs that have been underground for a year or more emerge at the surface, shed their cocoons, and make their way to whatever temporary water has accumulated. Within a day or two of their emergence, the night air of the outback is filled with a deafening chorus of frog calls, thousands of males calling simultaneously in a biological urgency that makes the entire desert seem to be vibrating with sound. The speed of their breeding is equally remarkable. Females select mates within hours of arriving at the breeding site, eggs are laid in the water within a day or two, and the tadpoles that hatch from those eggs develop at the fastest possible rate, racing to complete their metamorphosis into juvenile frogs before the temporary water disappears. Depending on conditions, this entire process from egg-laying to metamorphosis can be completed in as little as 2 to 3 weeks in the most ephemeral water bodies, a life cycle compressed to the minimum viable timeframe by millions of years of selection in an environment where time is always short and water never guaranteed. The ecological relationships that bind Australia's species together are as extraordinary as the individual animals themselves, and no account of Australian wildlife would be complete without exploring some of the most remarkable of these relationships in detail. Ecology is not simply a catalogue of species. It is the study of the web of interactions between those species, the partnerships, the competitions, the mutualisms and parasitisms and predator-prey dynamics that create, between them, a functioning ecosystem. And in Australia, these interactions often display a complexity and an intimacy that reflects the millions of years of shared evolutionary history between the species involved. Consider the relationship between the eucalyptus forests and the extraordinary diversity of nectar-feeding wildlife that depends on them. When a eucalyptus tree flowers, it produces prodigious quantities of nectar, more than most comparable flowering trees in other parts of the world. This nectar is the primary energy source for an astonishing array of animals, honeyeaters, the diverse family of nectar specialist birds that has radiated into dozens of species across the Australian continent, lorikeets and other parrots that have evolved brush-tipped tongues for extracting liquid nectar from flowers, pygmy possums that visit flowers at night, blossom bats that follow flowering events across the landscape with the same nomadic energy as the waterbirds follow rain, and countless insects of every description. All of these nectar feeders are, simultaneously, the eucalyptus tree's pollen vectors. As they push their beaks, tongues, snouts, or bodies into the flower clusters to reach the nectar, they inevitably become dusted with pollen, which they then carry to the next tree they visit. The eucalyptus depends on these animals for cross-pollination, and the animals depend on the eucalyptus for food, a partnership of mutual benefit that has been refined over millions of years into a relationship of extraordinary precision. Different eucalyptus species have flowers of different shapes, sizes, and chemical compositions, tailored to attract different pollinator species. And different pollinator species have physical and behavioral characteristics, tongue length, bill shape, body size, daily activity timing, finely matched to the flowers they visit most commonly. The honeyeaters deserve particular attention in this context. With more than 50 species in Australia alone, and a distribution that extends across much of the continent from tropical forests to arid scrublands, the honeyeaters represent one of the most spectacular evolutionary radiations in the bird world. They range in size from the tiny, jewel-like wee bill, barely 2 inches long, to the large and dramatic region honeyeater, with its extraordinary pattern of black and bright yellow scales. Their bills vary from short and stubby to long and dramatically curved, each shape an evolutionary solution to the geometry of a specific flower type. Some species are sedentary, maintaining year-round territories in areas where flowering is reliable and continuous. Others are highly nomadic, following the irregular, unpredictable flowering events that occur across different parts of the continent at different times, tracking flowering as a tracker follows a trail, responding to visual cues, chemical signals, and perhaps learn knowledge of productive areas. The region honeyeater, once common across the woodland areas of southeastern Australia, is today one of the most critically endangered birds on the continent. Its population has declined to somewhere between 300 and 400 individuals, a collapse so severe and so rapid that the species faces a challenge that goes beyond simple habitat loss. Region honeyeaters apparently learn their songs, or at least important components of them, from other members of their species. In a healthy, abundant population, young birds hear and learn the complex, melodic calls that are essential for mate attraction and territorial communication. But as the population has fragmented and individuals have become increasingly isolated from each other, many young region honeyeaters are growing up without hearing the songs they need to learn. They are developing abnormal vocalizations, simplified songs, or in some cases, songs borrowed from entirely different species. And birds with abnormal songs have dramatically reduced breeding success, because potential mates do not recognize them as suitable partners. This cultural impoverishment, the loss of learned behavioral traditions as population numbers fall, represents a conservation challenge that goes beyond the simple metrics of habitat and individual survival. It means that even if the habitat is restored and the immediate threats to survival are addressed, the population may struggle to recover its full functionality without active intervention to restore the cultural knowledge that has been lost. Conservation programs working with region honeyeaters now include captive populations where birds are deliberately exposed to recordings of correct song types, an attempt to preserve a cultural heritage as well as a genetic one. The birds of Australia represent one of the most extraordinary avian radiations on Earth, and to do justice to their diversity and remarkable adaptations would require a documentary series of its own. But let us pause on several of the most remarkable, because in their stories we find some of the purest expressions of Australian evolutionary ingenuity. The superb lyrebird, Menura novahollandi, is one of the world's great biological wonders. The male of this ground-dwelling bird of the southeastern Australian forests carries in his tail feathers one of the most spectacular ornamental structures evolved by any animal. The 2 outermost tail feathers are enormously elongated, curved into the shape of a lyre, the ancient stringed instrument for which the bird is named, and they frame an array of delicate, translucent filamentous feathers that together create a display structure of extraordinary beauty. When the male raises and fans these tail feathers during his elaborate courtship display, arching them forward over his head and vibrating them until they become a shimmering curtain of silver and brown, the visual effect is genuinely breathtaking, a piece of living art evolved by sexual selection over millions of years of female choice. But it is the lyrebird's voice, not its tail, that is perhaps its most extraordinary attribute. The superb lyrebird is the greatest vocal mimic in the natural world, a title contested by several other species but held most completely by this remarkable bird. It can reproduce, with extraordinary fidelity, the calls of virtually any bird species it encounters in its forest environment, the calls of species that share its territory and of species that are merely passing through. But its mimicry extends far beyond other birds. Lyrebirds have been documented accurately reproducing the sounds of camera shutters, the whirring of film cameras, the sound of chainsaws, car alarms, music heard near human settlements, and most famously, the calls of extinct bird species recorded in the 19th century that the lyrebird's ancestors heard and passed down through cultural transmission across generations. This last fact is not merely charming. It is scientifically profound. Lyrebirds appear to pass learned vocalizations from generation to generation, meaning that a lyrebird today may carry in its vocal repertoire sounds that were heard by its great-great-grandparents. This represents a form of non-genetic cultural inheritance, a transmission of learned information across generations, that parallels, in a remarkable way, the cultural transmission that plays such an important role in human societies. The study of lyrebird vocal culture is providing insights into the evolutionary origins of cultural transmission in animals more broadly, and into the complex relationship between genetic inheritance and learned behavior in shaping the traits that define a species. The male lyrebird's display is not only visual and vocal but intensely physical. He constructs a display mound in the forest, a raised platform of soil and leaves, and performs from this stage for hours each day during the winter breeding season. The performance includes not only the tailed display and the cascade of mimic calls and his own melodic song, but also elaborate physical posturing and movement, a total performance of extraordinary dedication and energy investment. Females visit multiple males and observe their displays over extended periods before choosing a mate, and the intensity of their evaluation is directly reflected in the complexity and quality of the male displays that selection has produced. The bowerbird represent another extraordinary chapter in Australian avian evolution. In this diverse family of birds, found primarily in Australia and New Guinea, the males have taken the principle of attracting females through display to a remarkable extreme. Rather than simply displaying their own bodies with elaborate feathers or behaviors, male bowerbird construct complex architectural structures, called bowers, that serve as the stage and context for their courtship displays. These bowers are not nests. They have nothing to do with egg-laying or chick-rearing, which occur in entirely separate, female-built nests. They are purely aesthetic constructions, built to attract and impress females, and the sophistication and artistry of the best examples are genuinely astonishing. The satin bowerbird, Tilenorhynchus violaceus, is among the most celebrated. The male builds an avenue bower, two parallel walls of sticks arranged vertically in the soil, creating a corridor through which he displays to visiting females. But the construction of the bower is only the beginning of his effort. The male then decorates the entrance and surrounds of his bower with a collection of objects, and here is where things become truly extraordinary. Satin bowerbirds show a pronounced preference for blue objects, a preference so strong that males will sometimes steal blue items from neighboring bowers rather than collecting their own. The natural blue objects available in the forest, blue feathers from other bird species, blue berries, blue flower petals, are supplemented eagerly by any blue manufactured objects that can be obtained near human habitation. Blue plastic bottle caps, blue straws, blue candy wrappers, blue pen caps, all are eagerly gathered and carefully arranged in the bower decoration. The male satin bowerbird also paints the interior walls of his bower using a mixture of charcoal, plant pigments, and saliva, applied with a small wad of plant material held in the bill, making it one of the very few non-human animals known to use a tool to apply a substance to a surface as a form of decoration. And beyond even the bower construction and decoration, the most impressive male satin bowerbird engage in a remarkable piece of visual manipulation. They arrange the objects in front of their bower in a specific pattern, with smaller objects nearest the bower entrance and larger objects further away, a pattern that creates the visual illusion of forced perspective, making the bower appear larger than it actually is when viewed from the position where a female stands during courtship. This phenomenon, called forced perspective bower decoration, was documented in a study that tested the arrangement experimentally and confirmed that females prefer males who maintain the size sorting pattern, suggesting that female bowerbird have evolved to evaluate male displays using a perceptual standard that goes beyond simple counting or color matching. In the rich, complex ecosystems of the Australian rainforest, the relationships between species reach their highest density and their greatest intricacy. The rainforests of Australia, particularly the ancient wet tropics of northeastern Queensland, are genuinely old. Parts of this system have been continuously forested for somewhere between 100 and 130 million years, making them among the oldest continuously existing forest environments on Earth. The plant families that grow here include lineages that predate the separation of Australia from the other fragments of Gondwana, lineages that were already ancient when the first marsupials were evolving in other parts of the world. In this ancient forest, the interactions between species have had correspondingly long to develop and refine. The mutualism between the southern cassowary and the large fruited trees that depend on it for seed dispersal, which we explored in Part 1, is one example. But the rainforest is full of such relationships, many of them still poorly understood, some still entirely undiscovered. The fig trees of the Australian rainforest are embedded in one of the most remarkable mutualisms in the natural world, a relationship so tightly co-evolved that neither partner can exist without the other. Fig trees produce their flowers inside a specialized structure called a syconium, which is the fleshy object we call a figure. The flowers are completely enclosed within this structure, inaccessible to most insects. The only pollinators that can reach the flowers are the fig wasps, tiny insects that enter the syconium through a minute pore at its base, moving through a passage so tight that they typically lose their wings and antennae in the process. Once inside, the female fig wasp lays her eggs in some of the flowers and pollinates others with pollen she carries from the figs she emerged from. The eggs develop into the next generation of fig wasps inside the syconium, which simultaneously develops into the mature fig fruit we recognize. The new wasps emerge, the females loaded with pollen, and immediately seek another fig of the right species in which to complete the cycle. Each species of fig is typically associated with one or a few species of fig wasp, creating a network of paired dependencies that has been evolving for at least 80 million years. The figs of the Australian rainforest are critical resources for an enormous diversity of wildlife, providing fruit year-round when other resources may be scarce. Cassowaries, pigeons, bats, possums, tree kangaroos, and a host of other animals feed on figs, and the disruption of the fig wasp mutualism, through any process that affected either partner, would ripple through the entire forest food web with consequences that are genuinely difficult to predict. The tree kangaroos of the Queensland rainforest deserve special mention in any account of Australian rainforest wildlife. These remarkable marsupials represent perhaps the most dramatic example of ecological reversal in the kangaroo family. The kangaroo family, Macropodidae, evolved as a group of ground-dwelling, hopping animals, and the majority of its members remain committed to that lifestyle. But in the rainforests of northeastern Queensland and New Guinea, a lineage of ancestral macropods climbed back into the trees, re-evolving arboreal adaptations that their ancestors had abandoned long before. The result is the tree kangaroo, an animal that combines the familiar kangaroo body plan, the powerful hind legs, the long tail, the characteristic marsupial reproductive system, with a suite of arboreal modifications that allow it to live, feed, sleep, and move entirely within the forest canopy. The Lumholtz tree kangaroo, Dendrologus lumholtzi, found in the rainforests of far north Queensland, is the most studied of Australia's two tree kangaroo species. It has a long, cylindrical tail that functions not as a spring for hopping, as in terrestrial kangaroos, but as a balancing organ for moving through the canopy. Its forelimbs are more developed and more flexible than those of ground-dwelling kangaroos, allowing it to grip branches and to move through the trees using a four-limbed gait rather than the bipedal bounding of its terrestrial relatives. Its hind foot has been modified for grip rather than propulsive power, with a broader, more flexible structure than that of ground kangaroos. And it moves through the canopy with a slow, deliberate, bear-like confidence that is utterly unlike the explosive, powerful locomotion of a red kangaroo on the open plain. The tree kangaroo feeds primarily on leaves, with fruit, bark, and flowers supplementing its diet. It spends much of its day resting in the canopy, conserving energy in the manner characteristic of folivorous mammals everywhere. Its role in the rainforest ecosystem includes seed dispersal, through the consumption and transport of fruit, and it serves as prey for the wedge-tailed eagle, Australia's largest bird of prey, which can take tree kangaroos from the forest canopy. The insects and other invertebrates of Australia constitute, by any measure of numbers or ecological importance, the true foundation of the continent's biological richness. For every kangaroo, every koala, every cassowary, there are trillions of insects, mites, spiders, worms, beetles, ants, termites, butterflies, and moths, and it is these small creatures that perform the essential ecological services upon which all visible wildlife ultimately depends. They pollinate the flowers, decompose the dead organic matter, aerate the soil, control plant populations through herbivory, and provide the base of the food chain upon which every insectivorous bird, lizard, frog, and mammal depends. The termites of Australia deserve particular attention, because in the Australian environment they perform ecological functions of outsized importance. There are more than 300 species of termite in Australia, ranging from tiny soil dwellers to the large species that construct the extraordinary cathedral termite mounds, those towering, sculpted structures of hardened clay that rise from the flat plains of the Northern Territory like abstract monuments, sometimes reaching heights of 15 to 20 feet. These mounds are among the most sophisticated structures built by any non-human animal, carefully engineered to maintain a near-constant internal temperature and humidity regardless of the extremes of the external environment, through a system of internal tunnels and chambers that creates natural ventilation and thermal regulation. The termite colony inhabiting one of these great mounds may number in the millions, and the collective biomass of the colony can exceed that of any mammal living in the same area. The termites function as the primary decomposers of dead wood and plant material in the Australian environment, processing enormous quantities of organic matter and returning the nutrients it contains to the soil in forms accessible to plants. Without termites, the nutrient cycling of the Australian ecosystem would be dramatically impaired. Dead wood would accumulate, nutrients would be locked up in unavailable forms, and the productivity of the entire system would decline. The termite mounds also serve as important habitat structures for other species. Perenties lay their eggs in them, as we noted earlier. Various lizard species shelter in the cavities of abandoned mound sections. Birds including gallas and corellas sometimes excavate nesting chambers in the hard clay walls of mounds. And small mammals, including the iconic numbat, a beautiful, striped marsupial that is one of Australia's most endangered species, rely on termites as their primary food source, spending their days digging into termite galleries and consuming the insects with a long, sticky tongue. The numbat, Myrmecobius fasciatus, is the only marsupial that is primarily diurnal, active during the day rather than at night. This unusual schedule reflects the activity patterns of its termite prey, which are most accessible in the warmth of the day when the galleries are most active. The numbat was once widespread across southern Australia but has been reduced by habitat loss and predation by introduced foxes and cats to a tiny remnant range in a few areas of southwestern Australia. Conservation breeding programs have established small, fenced populations at additional sites, but the numbat's recovery remains precarious. Australia's butterfly and moth fauna, while less studied than that of some tropical regions, includes many species of extraordinary beauty and biological interest. The cairn's birdwing, Ornithoptera euphorbium, is the largest butterfly native to Australia, with female wingspans that can exceed 7 inches. The males, smaller than the females but brilliantly colored in iridescent green and black, are among the most spectacular butterflies in the world. Their caterpillars feed exclusively on the Dutchman's pipe vine, a specific relationship that creates a conservation dependency between the butterfly and its host plant. In areas where the introduced species of Dutchman's pipe has displaced the native species, birdwing caterpillars feed on the introduced plant but are unable to complete their development successfully, a toxic case of ecological mismatch that has contributed to population declines in some areas. The story of Australia's wildlife cannot be told honestly without confronting the realities of the conservation challenges that this extraordinary biota now faces. These challenges are real, they are serious, and they have already resulted in biodiversity losses of genuinely tragic proportions. Australia holds the world's worst record of mammal extinctions since European settlement in the late 18th century. More than 30 species of native mammal have been driven to extinction since that time, a rate of loss unmatched on any other continent, and a further several dozen species are currently classified as endangered or critically endangered, their populations reduced to levels that make their long-term survival genuinely uncertain. Understanding why this has happened requires understanding the particular vulnerabilities of Australian wildlife and the particular nature of the threats that European settlement introduced. Australian mammals, having evolved in isolation from the aggressive placental predators that dominate other continents, had no evolutionary experience with the hunting styles and capabilities of cats and foxes. When European settlers brought these animals to Australia, initially as pets, companions, and for pest control, and when populations of both species subsequently established themselves in the wild, the consequences for native wildlife were catastrophic. The red fox, Vulpes vulpes, reached Australia in the 1870s, brought by settlers who wanted to recreate the fox hunting traditions of their homeland. Within decades, fox populations had spread across most of the continent, and the effect on small to medium-sized native mammals was devastating. Species that had survived for millions of years without any comparable predator had no behavioral defenses against an efficient nocturnal hunter that could follow their scent trails, run them down over short distances, and dig them from their burrows. Populations collapsed, and species after species disappeared from vast portions of their former ranges. The feral cat, Felis catus, has had an equally devastating impact. Cats have been established in Australia since the earliest days of European settlement, and today the feral cat population is estimated at somewhere between 2 and 6 million individuals, distributed across virtually the entire continent. Each feral cat kills, on average, somewhere between 1,000 and 2,500 native animals per year, a toll that, summed across millions of cats, amounts to billions of native animals killed annually. The cat's combination of extraordinary stealth, speed, and sensory capabilities makes it an almost perfect predator for the small marsupials and rodents of the Australian bush, and its adaptive ability to survive in almost any habitat from dense rainforests to the most arid desert means there is essentially nowhere for native prey species to escape its reach. The impact of introduced herbivores, particularly rabbits, sheep, cattle, goats, and camels, has compounded these predator-related losses through the wholesale transformation of vegetation communities. European rabbits, introduced in 1859 by a Victorian landowner who brought 24 individuals from England with the intention of providing sport hunting, reproduced with the speed for which they are famous and spread across much of southern Australia within decades, their population eventually peaking at an estimated 10 billion individuals. The grazing pressure of this population on native vegetation was catastrophic, degrading and destroying plant communities across millions of acres, and reducing the habitat available for native wildlife dependent on healthy vegetation structure. Feral camels, introduced as pack animals during the exploration of the interior in the 19th century and released when vehicles made them redundant, today number in the hundreds of thousands in the Australian outback. Feral pigs, introduced for hunting and as food animals, have established populations across much of the continent, and caused damage to habitats through rooting and wallowing, and predation on ground-nesting birds, reptile eggs, and small mammals. And the cane toad, Rhinella marina, introduced in 1935 in a misguided attempt to control cane beetles in Queensland's sugar plantations, has spread across tropical Australia in a wave of ecological damage, its powerful bufadienolide toxins killing the native predators, quolls, goannas, snakes, and others, that attempt to eat it. Species that have no evolutionary experience of toad toxins, and no behavioral avoidance of this deadly new prey item. The cane toad's spread is one of the most thoroughly studied and most discouraging examples of invasive species impact in the world. As the toad front advanced westward and northward from its Queensland origin point, populations of native predators in the path of advance were decimated within months of the toad's arrival. Freshwater crocodiles, which readily eat toads, have shown population declines of up to 77% in some areas. Goanna populations have collapsed across large sections of the toad's range. Quolls have disappeared from areas where they were previously abundant. The ecological reverberations of these predator losses continue to unfold in ways that researchers are still documenting. However, the story of the cane toad is not entirely without hope, because evolution is responding to the challenge in real time, and in multiple directions. Some populations of quolls in areas that have experienced toad arrival have shown rapid evolution of toad aversion, a learned or possibly genetic tendency to avoid attempting to eat toads. This behavioral shift, appearing within a few generations, suggests that natural selection can sometimes operate fast enough to produce adaptive responses to novel threats. Snake populations that coexist with toads have also shown evolutionary shifts in head size, with populations in toad-affected areas showing smaller heads relative to body size, a trait that prevents them from swallowing toads large enough to deliver a lethal dose of toxin. Against the backdrop of these losses, and in the context of the ongoing threats that continue to press upon Australia's wildlife, the conservation efforts mounted to protect the continent's biological heritage represent some of the most innovative, most determined, and most scientifically sophisticated conservation work being done anywhere in the world. Australian conservation science has, in many respects, led the world in developing practical responses to the specific challenges of island and isolated population conservation, the management of invasive species, and the use of fenced predator-free sanctuaries as refugia for threatened species. The fenced sanctuary concept has become one of the most powerful tools in Australian wildlife conservation. By enclosing large areas of native habitat with specially designed fences that exclude foxes, cats, and other introduced predators, conservation managers have been able to create spaces within which native wildlife can be reintroduced and allowed to recover without the continuous pressure of predation that prevents recovery in unfenced areas. The fences are typically more than 1.5 meters tall, with an inward curving overhang at the top and a buried section at the base to prevent digging, and they require regular maintenance and monitoring to ensure their integrity. But within them, native mammal populations that have been functionally extinct from the surrounding landscape for generations can be re-established and allowed to recover to densities that begin to approximate the ecological roles these animals once played. In some of the larger fenced sanctuaries, the recovery of native mammal populations has produced genuinely remarkable ecological restoration. When betongs, small marsupials related to kangaroos, are reintroduced into fenced areas, their digging behavior, as they forage for underground fungi and invertebrates, acts as a soil disturbance that significantly increases rainfall infiltration and seedling germination rates, enhancing the productivity and diversity of the vegetation community. When bilbies, larger desert marsupials that were once widespread across much of Australia, return to areas from which they have been absent for decades, the deep burrows they excavate provide shelter for dozens of other species. The recovery of an ecosystem following the return of its native mammal community is not simply additive, not simply a matter of more species being present. It is a transformation, a restoration of processes and relationships that have been absent, sometimes for generations, and that are essential to the full functioning of the system. The fight against the Tasmanian devil facial tumor disease has produced some of the most moving and most technically sophisticated conservation efforts in recent Australian natural history. The Insurance Population Program, which established groups of healthy, disease-free devils in carefully managed facilities and on offshore islands, has now accumulated several thousand individuals representing the genetic diversity of the wild population before disease-related bottlenecks could reduce it. These insurance populations are managed with sophisticated genetic protocols designed to maintain maximum heterozygosity, the genetic variation that provides the raw material for evolutionary adaptation, including the potential development of disease resistance. And there are signs, tentative but real, that the wild devil population may be developing some resistance to the tumor disease through natural selection. In some long-affected populations, there are individuals that appear to survive the disease longer than average, or that mount partial immune responses to the tumor cells. The frequency of certain immune gene variants that may confer partial resistance appears to be increasing in these populations, exactly the pattern that would be expected if selection were acting on heritable variation in disease response. The possibility that the Tasmanian devil population could evolve its way through this crisis, guided by natural selection acting on naturally occurring genetic variation, is one of the most encouraging findings in recent Australian conservation biology. The conservation of sea turtles in Australian waters provides another example of dedicated, long-term conservation effort producing meaningful results. The green sea turtles of the Great Barrier Reef and Coral Sea, and the loggerhead turtles of the eastern Australian coast, have benefited from decades of nest protection programs, bycatch reduction efforts in commercial fisheries, and the establishment of marine protected areas. Populations of both species show signs of stability or slow increase in areas where these protections are in place, though both face ongoing threats from pollution, entanglement in fishing gear, and the long-term challenge of climate change affecting the temperatures of nesting beaches and the sex ratios of hatchlings. The dugong, that gentle sea cow of Australia's northern and eastern waters, is also the subject of intensive conservation attention. Australia holds the second largest dugong population in the world, and protecting this population requires the maintenance of the extensive seagrass meadows on which the species depends. Seagrass communities are sensitive to increased water turbidity caused by runoff from agricultural and urban areas, to physical damage from boat propellers and anchors, and to the large-scale die-offs that can occur following cyclones and floods. Managing these threats in a landscape where agriculture and coastal development are economically significant activities requires careful negotiation between conservation goals and other social and economic priorities. Among the most fascinating recent developments in Australian conservation has been the growing recognition of the central importance of Indigenous ecological knowledge to effective conservation management. The Indigenous peoples of Australia have lived on this continent for somewhere between 50,000 and 65,000 years, the longest continuous occupation of any continent by a human population. Over this extraordinary span of time, they developed, through direct observation, experimentation, and accumulated intergenerational transmission of knowledge and understanding of the Australian environment of enormous depth and sophistication. This knowledge encompasses not only the identities and behaviors of individual species but the dynamics of whole ecological systems, the patterns of fire and regeneration, the indicators of seasonal change, the signs that predict flooding or drought, the relationships between species that ecological science has only recently begun to document. It includes knowledge of plant medicines, of the locations of water in dry landscapes, of the timing of animal breeding seasons, of the behavioral cues that signal the movements of prey. And it includes knowledge of how to manage landscapes through fire, how to use deliberately set fires as tools to promote the growth of specific plants, to drive game, to maintain the mosaic of different age vegetation patches that maximizes overall biodiversity. This practice of cultural burning, also sometimes called fire stick farming or cool burning, has attracted intense scientific attention in recent decades as researchers have begun to recognize its ecological sophistication. The fires set by Indigenous land managers are typically smaller, cooler, and more precisely targeted than the large, hot, uncontrolled fires that burn when fuel loads accumulate over long periods without management. They create a patchwork of burned and unburned areas across the landscape, providing the habitat diversity that a wide range of species require. Some animals need the open, herb-rich ground of recently burned areas. Others need the dense cover of longer unburned vegetation. And many species require both at different stages of their lives or in different seasons. The mosaic created by cultural burning provides all of these habitat types within a landscape, maintaining biodiversity at a level that unmanaged landscapes cannot match. The return of Indigenous burning practices to Australian land management, in partnership between Indigenous communities and government and conservation agencies, is now recognized as one of the most promising tools available for maintaining the health and biodiversity of Australia's landscapes. Projects across northern Australia and increasingly in southern parts of the continent have demonstrated that landscapes managed with cultural burning show greater plant diversity, higher populations of threatened native mammals, and reduced frequency and severity of the large, damaging wildfires that occur when fuel loads are allowed to accumulate unchecked. The knowledge of Australia's Indigenous peoples extends to many other dimensions of conservation relevance. Knowledge of seasonal indicators, the flowering of specific plants signaling the breeding season of certain fish, the behavior of certain bird species indicating the approach of rain, has practical applications for wildlife management. knowledge of the locations of permanent water, of rare plant species, of important habitat features that may not be apparent to observers without long familiarity with the landscape, is of direct relevance to conservation planning. And the frameworks through which indigenous communities understand their relationships with the land and its wildlife, frameworks of custodianship and responsibility that are fundamentally different from Western frameworks of ownership and resource exploitation, offer philosophical perspectives that enrich and challenge the way conservation science approaches its goals. As we look toward the future of Australian wildlife, we are confronted with a landscape of genuine uncertainty, extraordinary challenges, and genuine reasons for hope. The challenges are real and serious. Climate change is already affecting the Australian environment in measurable ways. Average temperatures across the continent are rising. The frequency and intensity of extreme heat events is increasing. Drought periods are becoming longer and more severe in many regions. The frequency and severity of large bushfires is increasing as a result of hotter, drier conditions and more frequent extreme fire weather. The Great Barrier Reef, arguably the most biologically diverse marine ecosystem in the world and home to an extraordinary assemblage of coral, fish, marine mammals, reptiles, and invertebrates, has experienced unprecedented coral bleaching events in recent years as ocean temperatures rise, with bleaching occurring across the entire reef system and causing coral mortality on a scale never previously recorded. The implications of these changes for Australia's wildlife are complex and in many cases genuinely alarming. Species that have evolved over millions of years in highly specific environmental conditions may find those conditions changing faster than evolutionary processes can respond. Animals with narrow thermal tolerance ranges may find their habitable zone shrinking as temperatures rise, unable to move fast enough to track their preferred conditions or finding that suitable habitat in cooler areas is blocked by geographic barriers or fragmented by human development. Plants whose flowering and fruiting timing has been calibrated over thousands of generations to the specific seasonal cues of their environment may find those cues decoupled from the conditions that actually favor pollination or seed dispersal, disrupting the intricate mutualistic relationships that hold ecosystems together. The mountain pygmy possum, Burmese parvus, provides a sobering example. This tiny, beautifully furred marsupial, the only mammal endemic to the Australian alpine zone, spends its winters in hibernation beneath the snow, which provides insulating protection from the extreme cold of the alpine winter. As climate change reduces the depth and duration of snow cover in the Australian Alps, the insulating layer that protects hibernating mountain pygmy possums is becoming less reliable, and the animals are experiencing increased mortality during mild, snowless periods when they are exposed to cold without insulation. Their food supply, critically dependent on the mass emergence of bogong moths that migrate to the Alps each summer to estivate in rock crevices, has also been disrupted by warming and drought conditions in the moths' breeding grounds further inland. The golden bowerbird of the Queensland rainforest, which builds its remarkable display tower at specific altitudes in the cool upland forests, faces a similar altitudinal squeeze as its preferred cool climate habitat shrinks upward on the mountain slopes with rising temperatures, with no higher ground available when the mountain tops are reached. The same challenge confronts dozens of other species confined to the cool, wet mountain environments of southeastern Australia and the upland tropical rainforests of Queensland. Yet alongside these challenges, there are also real and compelling reasons for hope. The resilience that Australian wildlife has displayed throughout its long evolutionary history, the capacity to survive and recover from the extremes of fire, flood, drought, and long-term environmental change that have characterized the Australian environment through geological time, is not nothing. It is a biological heritage of profound depth and demonstrated effectiveness. Species that have survived the upheavals of millions of years are not without resources when confronting new challenges, even challenges of the speed and scale that climate change presents. And the human response to these challenges, while far from adequate, is real and in many cases genuinely innovative. The expansion of protected area networks to encompass a greater proportion of Australia's biodiversity. The development and deployment of humane baiting programs that have dramatically reduced feral fox and cat populations in large areas of high conservation value. The establishment and management of fenced predator-free sanctuaries that are providing refugia for threatened species. The reintroduction of locally extinct species to areas from which they were lost. The development of conservation genomics tools that allow managers to make informed decisions about the genetic management of small, isolated populations. The growing partnership between conservation science and indigenous knowledge. All of these represent genuine investments in the future of Australian wildlife. The ongoing research into innovative solutions to specific conservation challenges is also a source of optimism. Scientists are investigating the possibility of developing oral vaccines against the devil facial tumor disease that could be deployed in wild populations. Researchers are experimenting with training techniques to teach native predators, quolls and others, to avoid cane toads through conditioned taste aversion, giving them behavioral defenses that evolution has not had time to provide. Geneticists are exploring the possibility of introducing, through careful selective breeding, the few alleles that appear to confer partial resistance to devil facial tumor disease more broadly throughout the devil population. Conservation horticulturalists are propagating and replanting the large fruited tree species of the Queensland rainforest that depend on cassowaries for seed dispersal, maintaining populations of these trees in areas where cassowary numbers have fallen too low to provide adequate dispersal services. Marine biologists are experimenting with coral-assisted evolution programs, identifying and breeding coral genotypes that show greater tolerance of elevated water temperatures and working to incorporate these tolerant genotypes into reef restoration plantings. None of these efforts is a complete solution. None of them, individually or collectively, can simply undo the damage that has been done or halt the broader environmental changes that are driving so much of the current conservation crisis. But together they represent a serious, scientifically grounded, and ethically motivated response to a genuine emergency, and they give wildlife and the scientists and communities working to protect it a fighting chance. Let us now return, for a moment, to where we began. Let us stand again at the edge of the great Australian desert, at that moment when the sky has been building for days and the first fat drops of rain are beginning to fall. The red soil beneath our feet darkens as the drops hit, each one releasing a brief, sharp exhalation of petrichor, that remarkable smell of rain on dry earth that is produced by the volatile compounds released from soil bacteria and from the oils that eucalyptus leaves have deposited in the dust over weeks of drought. Around us, the animals are responding. A mob of red kangaroos, which has been resting beneath the sparse shade of some mulga trees through the heat of the afternoon, lifts their heads almost simultaneously, ears rotating forward, nostrils testing the rain-scented air. A Perentie lizard, which has been motionless on a sun-warmed rock for 3 hours, suddenly becomes animated, tongue flickering rapidly as it reads the changing chemical landscape. Somewhere beneath our feet, in the hardened clay 10 inches below the surface, a water-holding frog registers the change in soil moisture and begins the slow biochemical reactivation that will bring it back to full function within hours. In a burrow nearby, a family of bilbies, their satellite dish ears folded down in sleep, begin to stir. The rain is intensifying now. What began as scattered drops has become a steady fall, and within the hour it will be a downpour, filling the dry creek beds with churning red water, penetrating the soil to depths it has not reached in months, triggering the germination of seeds that have been waiting since before the last wet season ended. The desert is not dying. The desert is not even sleeping. It is merely waiting, as it has always waited, with the deep patience of something that has been doing this for 45 million years and knows, with a certainty encoded into every genome of every species that has survived here, that the rain will always come again. This is the fundamental truth about Australia and about its extraordinary wildlife. It is a continent built for extremes, and its creatures are built for extremes in return. The red kangaroo's tendons that store energy in their elastic embrace. The thorny devil's capillary skin that drinks from dew. The platypus's electric bill that finds life in darkness. The lyrebird's brain that holds the songs of extinct species in living memory. The water-holding frog's body that keeps itself alive for years on its own stored water. The eucalyptus tree that burns and rises again from its lignotubor like a biological phoenix. The termite colony that maintains a stable climate inside its clay cathedral, while the world outside bakes and scours. The bandicoot's backward-facing pouch that keeps soil out of the nursery while mother digs. Every one of these solutions, every one of these biological innovations, is a story of life confronting impossible conditions and finding a way. Finding not just survival, but elegance. Not just persistence, but extraordinary, breathtaking, staggering beauty. The beauty of function perfected. The beauty of a billion years of trial and error, of selection and adaptation, of species and environments shaping each other across geological time into a system of such intricate, such precise, such living complexity that the more closely you look at it, the more you see, and the more you see, the more you understand how much remains to be seen. Australia is, in the truest and most literal sense, a continent of wonders. Its red deserts and green rainforests, its ancient rivers and temporary lakes, its coral seas and alpine meadows, its booming billabongs and whispering mulga plains, are home to forms of life that exist nowhere else on Earth, that have never existed anywhere else on Earth, that represent evolutionary paths taken once and only once in the history of life on this planet. To lose them, to allow them to disappear through carelessness or indifference, or the accumulated weight of 1,000 small and large destructions, would be to close a chapter of the book of life that can never be rewritten. We began this journey with a simple statement. Australia is a continent so ancient, so isolated, so magnificently strange, that the creatures living upon it seem to belong to a different world entirely. Having traveled together across its landscapes and through its extraordinary cast of biological characters, we hope that statement now carries more weight. We hope that the red kangaroo now means something more than an icon on a postage stamp. We hope that the platypus is now something more than a children's book curiosity. We hope that the Tasmanian devil is something more than a cartoon character, that the cassowary is something more than an exotic bird, that the thorny devil is something more than a spiky lizard, that the lyrebird is something more than an impressive party trick. They are all of them, and the thousands of other species we have not had time to explore in detail, each of them the product of an unbroken evolutionary lineage stretching back to the beginning of life itself. Each of them carrying in its genome the record of every environmental challenge its ancestors faced and solved. Each of them a living library of solutions to the problems of existence in one of the most demanding environments on Earth. Each of them irreplaceable. The story of wild Australia is not a story that has ended. It is a story that is still being written, in the genetic code of species still evolving, in the ecological relationships still developing and changing, in the conservation battles still being fought, in the research laboratories and field stations and indigenous land management programs where people are working, with genuine dedication and genuine intelligence, to ensure that this story continues. And it is a story in which all of us, wherever we are watching from, whatever time we are watching at, have a stake. Because the living world of which Australia's biota is such an extraordinary part is the living world of which we too are part. The systems that maintain life on this planet, the cycling of water, of carbon, of nitrogen, the regulation of climate, the purification of air and water, the maintenance of the soils that grow the food that sustains human civilization, all of these services are provided by the biodiversity of the natural world, maintained by the web of species interactions that makes ecosystems function. When species are lost, when ecosystems are degraded, these services are diminished, and the consequences extend far beyond the loss of the species themselves. The kangaroos bounding across the red plains, the cassowaries moving through the ancient rainforest, the sea turtles navigating by moonlight to their ancestral beaches, the platypuses hunting by electric scents in dark mountain streams, all of them are part of a whole that is larger than any of its parts, a whole that has been assembling itself for hundreds of millions of years, and that gives back to the world, and to us, far more than we have yet fully appreciated or understood. Australia's wildlife is one of the great treasures of the natural world. Extraordinary in its origins, astonishing in its diversity, magnificent in its adaptations, and worthy, in every measure that we have the ability to apply, of our deepest respect, our most active protection, and our most enduring fascination. The red kangaroo is still bounding. The rain is still falling on the red desert. The lyrebird is still singing in the ancient forest, its voice carrying the memories of extinct birds in a chain of living sound that stretches back further than recorded human history. Australia is still wild. And as long as we pay attention, as long as we refuse to look away, as long as we bring to this extraordinary continent the respect and the wonder that it so completely deserves, it will remain so.